Okay, thank you very much for the nice introduction. And good afternoon again, everybody. So again, welcome to Japan. So it's my great pleasure to have all of you here since 5 years. So in the first half of my talk, I will briefly talk about, introduce our RIKEN Center for Advanced Intelligence project. Then after that, let me talk about our team's research activities. Okay, so my talk always starts from this one, and this is the most important slide. So what is RIKEN? So name in Japanese, actually, our institute is written in this way, 6 characters. Then the first 3 characters are pronounced as Rikagaku, and the last 3 characters are pronounced as Kenkyūsho. And the first 3 characters means physics and chemistry, basically. Then the last 3 characters is research institute. And many years ago, in English, RIKEN was called Research Institute for Physics and Chemistry or something like that. But of course, RIKEN is no longer only doing physics and chemistry, but like biology and AI, supercomputer, and more. Then, 6 characters in Japanese is actually too long, and nobody calls us Rikagaku Kenkyūsho, but people take the first character and fourth character and attach them. So this is pronounced as RIKEN in Japanese, and ordinary Japanese people call us RIKEN. Then at some point, RIKEN headquarters decided to use this Japanese acronym as official English name. So this means in English, so we are no longer Research Institute for something, but we are RIKEN. So this is our official name. So this is the most important take-home message for you. And RIKEN actually has a relatively long history. So it started in 1917 as a private foundation, actually. And actually, Emperor's family also donated some initial money and something like that. And this Shibusawa Eiichi is nowadays a very famous person, and he's a kind of father of Japanese industry or something. He also donated some money. Then, so in 1933-39, RIKEN was actually a quite big entity, and it's called RIKEN Concern, and had 63 companies and 121 plants. It was really a big entity. But because RIKEN was big, so it was regarded as a dangerous entity. And after the World War II, RIKEN was broken up. But in 1948, so RIKEN restarted as Scientific Research Institute Limited. And then, so we became public corporation and the National Research Center now. And we had a new president, Gonokami, from last year. And he was actually a former president of the University of Tokyo. So we will have actually more collaboration with the University of Tokyo nowadays. So then entire RIKEN has 2,900 researchers and 500 admin staff. So it's really a big entity. And we have 15 research centers and programs, platforms, and etc. And roughly 6 physics-related centers, and 6 life science and medicine-related centers, and 3 are about informatics. So one is actually about robotics, and second one is about supercomputer, high-performance computing, and our Center for Advanced Intelligence project. So this is the entire RIKEN. Then RIKEN is also quite international, and we have more than 800 international researchers coming from 65 countries and regions. So also a lot of people from Europe and Italy here. So I can't see the clear number here because it's alphabetical order. But maybe we don't have so many Italian researchers so far. So but through this workshop, hopefully we can have more communication and collaboration. So then what is RIKEN AIP? So this is our center. So we started RIKEN AIP in 2016 under the Ministry of Education, Culture, Sports, Science, and Technology. And now we are in our Nihonbashi office. But we have distributed office across Japan because several teams are located in different universities from Sendai to Kyoto, Nara, and Fukuoka. Then we have 3 research groups. And the first group is called Generic Technology Research Group. And here we have 13 teams. So they are working on learning and inference algorithms like robust inference and Bayesian inference, high-dimensional estimation, and statistical and optimization theory. So they do the convergence analysis and non-convex optimization analysis and things like that. Then the second group is working on, is called Goal-Oriented Technology Research Group. And here we have 17 teams. So roughly we have two pillars here. And the first pillar is about AI for science. So they work on topics like cancer research, material science research, genomics research. The second half is about AI for societal problems, like natural disasters, elderly healthcare, education, and things like that. Then the last group is called AI in Society Research Group, and we have 6 teams here. So they do more like a society issues like personal data management, AI security, economy and management, ethics and governance, things like that. So we have 3 groups here. And in total, so we have about 100, so I don't know whether this is the exact number, 137 employed researchers, and 40% are international researchers, and 22% are female researchers. So still, we need to improve the diversity, but inside Japan, so this is quite good, actually, in terms of diversity. Then we have 284 visiting researchers, 96 domestic students, and 156 international interns. So we stopped internship program in the last 3-4 years due to COVID-19, but we resumed the program and we started to accept intern students from last year and also this year. So hopefully we can also invite internship students from IIT. Then, so maybe I don't really go into the detail here, but we do some theoretical research and accelerating scientific research and solving socially critical problems, and also studying AI ethics and legal issues like this. So these are a rough overview of RIKEN AIP. Okay, good. Then the first part was done. So then the second part is about my team. So it's called Imperfect Information Learning Team. And we are working on basically robust machine learning. And we made, I think, a lot of progress in the last 4 or 5 years. So I would like to briefly introduce our recent advances in robust machine learning. And in our team, so we are interested in developing novel machine learning algorithms that allow reliable learning from limited information. So nowadays, so it's the era of big data. So in many cases, we can have a huge amount of data. Then, so learning itself is rather straightforward. So in that case, like speed and efficiencies, computational efficiency is more important. But our team focuses on like limited information situation. Because still in like many applications, so we are not so free to obtain label data. So like learning from weak supervision, or learning from like noisy labels, or learning from biased data. So these are still important challenges in many real-world applications. And we have like 6 members and many great visiting scientists and part-timers, interns. So they are really doing great jobs. Okay, then so I would like to talk about 3 topics briefly. And then finally, so I would like to talk about our recent challenges. Then let me start from weakly supervised learning. So this is one of the favorite topics in our team. And we are aware that so supervised classification from big label data is already quite successful in speech, image, language, like online advertisement, and etc. But still, in many other applications where in which big label data is not available, like in medical research, natural disasters, and robotics also, brain signal analysis, in many applications, collecting label data is extremely expensive, or sometimes impossible in the case of natural disasters, for example. So we care such a situation. But so I wanted to say in the beginning, so we want to train a classifier only from small data. But learning from small data is not generally possible. So statistically, so we need a large number of data to reduce the variance. So instead, so we decided to use weak supervision that can be collected easily. So we don't say we train a classifier from small samples, but we have something big. But that big data is weak in some sense. But still, like number n is quite large. So we can still use like a large sample analysis in that situation. And the typical example is called PU classification, positive unlabeled classification. So it's a binary classification problem. So we want to solve this problem. So given positive and negative data, we want to separate them. It's the simplest machine learning problem. But in this PU scenario, we only have positive data and unlabeled data without having any negative data. So we only have blue points and black points, but still we want to separate blue and red. So this is PU classification. And we have been working on this topic for already 10 years, and we have a nice theory and algorithm with some nice applications. So this was almost solved already. So we can now solve a classification problem only from PU data without having any single negative data. So here's a successful application so we had last year. It's about signal enhancement or signal denoising. So it's the simplest problem. So we have noisy signal and we want to just remove noise. Like this is noisy speech basically. So this is the problem. And in standard approach, so people prepare so-called parallel training data. For the same signal, they want to have clean version and noisy version. Then based on this, they do supervised learning. By that, they can remove noise. So that's the standard approach. But in reality, so it's not possible to obtain the parallel data. So then usually people prepare like synthetic noise and add this synthetic noise to clean signal. Then by that, they can have like a noisy version and clean version and train a classifier. But so this synthetic noise is not always realistic enough. So the obtained system is not generalizing so well in reality. Then in our method, we simply use PU classification. And in this setting, so the positive class is actually noise. So we just put microphone in some noisy environment and just record noise, environment noise. So this is already positive data, so it's labeled. Then, so in the same environment, so somebody speaks. Then we can collect so the mixture signal of noise and speech. So this is actually regarded as unlabeled data. It's a mixture of positive samples and negative samples. So positive in this case means noise, and negative in this case means signal. And noisy signal is a mixture of these two. Then it's done. So we have a set of positive data, and we have a set of unlabeled data. So it is really this problem. So then only from blue points and black points, we can separate blue and red. And we can extract this speech, clean speech, only from PU data. So this is a very simple approach, but we can really solve the problem directly without really preparing synthetic data. So that's a kind of nice usage of PU classification. Then, so this idea of PU classification can be extended to actually many different weakly supervised learning problems, like learning from positive confidence data, or learning from two sets of unlabeled data. So this is actually quite interesting. So it's a supervised learning problem, but we don't have any single labels. But instead, we are given two sets of unlabeled data, but class priors are different. Like in the first set, let's say, so we have 80% positive and 20% negatives. But in the second set, we have like 30% positives and 70% negatives or something like that. So we only know the proportions, but we don't have any single labels. But we can prove that only from two sets of unlabeled data, we can actually solve a classification problem. So like a hypothetical scenario is that like there are two hospitals and they have large number of medical images. But medical doctors are so busy, so all medical images are unlabeled. But suppose we have some prior knowledge that okay, hospital A has like 30% cancer patient and hospital B has 20% cancer patient or something like that. Then in principle, only from like unlabeled medical images and these proportions, we can actually solve a classification problem, at least mathematically. Maybe in reality, we should have more challenges, but we can solve the problem in principle. So that's UU classification. And dissimilar classification is actually a special case of this UU classification. But it's a like sensitive prediction problem. And sometimes we can't easily obtain labels, like question about your salary or your religion or political opinions. People don't really want to say yes or no. But instead, they may say, okay, my opinion is the same as that person, or my opinion is different from that person, or something like that. So these are like similar data pairs or dissimilar data pairs. And this is quite popular in clustering community. But we can really use similar, dissimilar information for supervised classification. And we can have a convergence guarantee for this scenario. And finally, so we had a book on this machine learning from weak supervision. So we also have a lot of extensions for multi-class problems. But interestingly, so methodologies are basically the same. So that's the beauty of this framework. So we construct many different problems, but basically, so we have a very simple recipe to solve the problem. Okay, that was about weakly supervised learning. So we've done already 10 years and we had reasonably good results. Then the next topic is learning from noisy label, so noisy robust learning. So let's consider, again, a very standard supervised learning problem with noisy output. So in the case of regressions, we have horizontal axis input X and vertical axis output Y. Then we have output noise like this. Then we try to have like a regression function like this. So we do like standard least squares or something. So that's the regression case. Then in the classification case, maybe labels are flipped. Like in principle, we have all blue points here, but because of label noise, we have some different labels here and here, like in this way, mixed. And usually we don't really care. So we just collect a large number of like noisy labels and try to train a regressor or classifier. So this is a standard problem. So hasn't such a classical problem already solved? And for regression, yes. So by assuming noise is additive, mean zero additive noise, then just we need large number of data. So noisy big data is statistical consistency. So as long as you have many noisy data points, then noise is basically canceled out automatically. And just fitting noisy data gives you the optimal solution in the end. But actually for classification, it is not true. So even if you have infinitely many noisy labels, still like your solution is not optimal in some case. So we need a specific noise reduction mechanism to achieve statistical consistency. So this is a very simple problem that everybody knows, but it's surprising that this was not really solved yet. Then, so one direct approach to address this issue is to use noise transition matrix. So T here. So basically, noise transition matrix describes the probability of flipping clean label to noisy labels. Like in the 3-class case, we have a 3x3 matrix like this. Then 1, 0, 0 means class 1 label is always class 1. So this is a good case, noiseless case. But 0.1, 0.8, 0.1. So this means class 2 label is true only with 80%. And this flips to class 1 or class 2 with 10% probability. Then, so the bottom one, so 0.5, 0.50. So this is really a stupid case. That class 3 label is never true. And it is always class 1 or class 2 with 50%. It's really the worst case. But noise transition matrix T describes this kind of probability. Then, so not from our team, but from another group. So there was a very nice paper that uses this noise transition matrix to really solve the noisy classification problem. So they proposed 2 approaches. The first approach is to use T, or T transpose to be precise, to simulate the noise. So once we apply our classifier to T transpose, then we can basically simulate noise. Then to this noisy classifier, we just fit noisy labels. Then okay, we can recover consistency. It's a very natural approach. Then the second approach is the other way around. So T is like noise process. Then T inverse is actually a denoising process in a rough sense. Then if we apply T inverse to the loss function, then actually we can eliminate noise. Then by that we can recover statistical consistency. So once we have T, then either applying T transpose or T inverse, we can get rid of the influence of noise systematically. So that's a beautiful theory here. But the problem is that this T matrix is unknown in practice, and we should estimate it from noisy data. only from noisy data. And this is actually not mathematically solvable, unfortunately. So we need some additional assumption or some special heuristics to solve the problem. And we spent several years to consider some heuristics or some ideas. And in the end, so we came up with a nice idea to estimate t under relatively mild condition. And to the best of our knowledge, so this is the best method to estimate t in this framework. And I don't really go into the detail here, but it's called volume minimization. So true noise transition matrix can be actually expressed in a triangle like this, in the 3-class case. Then our noisy labels, noisy training data actually are included in this triangle. Then our solution is to obtain a triangle that contains all noisy labels and having the minimum volume. So minimum volume is expressed by this regularizer. Then by solving this problem, so we can recover the true triangle if we have like noiseless labels, or otherwise, as long as our noisy labels are reasonably scattered. So this is like a mathematical term, but I don't really go into the detail. But our noisy data is reasonably scattered, then we can actually identify true t only from noisy label. This is a quite simple approach, but it has theoretical guarantee to solve the problem. Okay, great, we solved the problem. So this was the kind of end of the story I want. But in reality, so noisy labels are much more complex, because our simplified formulation on this page was so-called class conditional noise, or input independent noise. So noisy labels are determined only by the true label. So this means, so everywhere in the input space, noise properties are the same. But in reality, perhaps so points near the decision boundaries are quite difficult to label, but points far away from the decision boundaries are quite easy. So then, so noisy labels are usually input dependent in the real world. So then in that case, so we need to model input dependent noise transition matrix function. So now t is a function of x. So even if t is a constant matrix, solving a problem was already difficult enough, and we had a reasonable solution. But it may not be possible to extend that theory to like noise transition matrix function. It's too difficult. Then we decided to introduce some heuristics to solve the problem. Like t can be decomposed into some parts, or we use some additional confidence scores, or we assume that t is smooth over some manifold or something like that. So by that, so under some condition or for some data set, so we can obtain a good solution, but not always, because it's heuristic based. So we did some effort to solve this problem, but still like we couldn't really solve the problem completely yet. And I will come back to this point later, because we decided to take a completely different approach to this problem in the end. And one side story here is that we also had a completely independent line of research for handling noisy labels. And this is completely heuristic, but it's memorization based. So it is known that neural network can memorize clean data faster. Suppose we have like noisy data set like this, then so after a few iterations, we can easily obtain this solution. But if we want to completely fit noisy labels to obtain this one, so we need more iterations. So that's clear. So then, so stochastic gradient basically fits clean data faster than noisy data. So this means, so let's do RE stopping. So that's a like good old heuristic. But implementing RE stopping in the right way is actually very difficult, because it heavily depends on the data set and many other situations. So everybody knows RE stopping is useful, but implementing it in the right way is very difficult. Then our idea is quite simple. So we propose to use two neural networks that are copied. Then so we let them teach each other. So basically, two neural networks are trained independently. Then so after a few iterations, we select samples that have smaller loss. So this means they are clean, so they're supposed to be clean samples. That's why they are fitted area. Then select those like small loss data and like neural network A select those small loss data and teach them to B. And same thing goes for B. B select some data and just teach it to A. And this is repeated until convergence. Then in the end, only clean data are selected, and finally we obtain a clean solution. So that's a simple approach. Then later on, we found that so only teaching disagreed data between two neural networks can even enhance the generalization property. And also, so we had a very nice heuristic to use large loss data. So small loss data is regarded as clean samples. So that's why we selected them and teach them to another network. But large loss data are supposed to be like noisy labels. And if we know they are noisy, they also have some information to improve the performance. And our basic idea is, so if we fit these like large loss data, then after some iterations, our solution will be trapped by some poor local optimum. So basically, so knowing, like having large loss data is a kind of nice precaution for overfitting. Then, so we know that if we follow this gradient, so we will suffer the problem later. Then, so let's do the gradient ascent. So let's do gradient ascent back, because going down the slope is dangerous. So let's escape from that local optimum. Then, so once we take one step back and select another minibat here, and then it's stochastic. Maybe the next direction is slightly different. Then, so we continue the process. By that, so intuitively, so we can like escape from poor local optimum. And there's no theory, but it works really well in many applications. Like in some benchmark experiments, so we randomly flipped 50% of the labels. Still, the solution does not overfit, and it converts to the right solution. So that's a nice heuristic, but it works quite well in many problems. Okay, then the last topic is about transfer learning. So it's a standard problem. So training and test data follow different distributions, and we want to adapt our predictor to the test domain. Maybe different distributions are caused by changing environments over time, or nowadays maybe privacy concerns is more important. We are not allowed to collect data as we want. Then our training data is often biased compared to the test data. So we want to adjust this bias. And transfer learning, the aim of transfer learning is to train a test domain predictor using training data from different domains. And it's not a new problem. Actually, I co-organized the workshop already in NIPS 2006. And at that moment, actually, there was no name for this problem. So we had a very long title, NIPS workshop on learning when test and training inputs have different distributions. So it was one of the longest titles of the workshop. But this workshop was actually quite successful. And we had a lot of great talks. And after 3 years, we published an edited volume from the MIT Press. And nowadays, this book is cited a lot, actually. So this topic is becoming hot now. And in this book, we named the problem dataset shift. But now it's called distribution shift. So maybe distribution shift is a nicer name. So there was actually already a distribution shift workshop at NeurIPS in the last 3 years. So this topic is becoming more important nowadays. So let me briefly talk about some basics of this transfer learning problem. And for illustration, let's consider the problem called covariate shift. So covariate is the name of input in statistics. So covariate shift basically means input distribution changes, P of X changes. But the rest, P of Y given X, does not change. And this can be nicely illustrated in regression. So like this is one-dimensional regression. Horizontal axis is the input, and the vertical axis is the output. And we have the target functions, red one. So this is unchanged. But the input distribution changes. So training inputs are coming from the left-hand side. So we have blue points for training. But test inputs are located on the right-hand side. So then we have test points here. It's a kind of like extrapolation problem. So from blue points, we want to predict black crosses. But naively, if we perform like linear least squares, then we end up in just having this green line. So this fits blue points perfectly. but it doesn't predict black crosses well. And statistically, we can easily show that this ordinary training, ordinary d-squares, is not statistically consistent. But once we have importance here, so this is importance-weighted d-squares, importance-weighted training, then so only from blue points we obtain this green line, and it predicts black crosses quite well. So that's importance-weighted training, and that's the basic technique used in transfer learning and covariate shift. And here, importance is the ratio of px, p test of x over p training of x. And in this example, actually, for most of the blue points, importance is almost 0 on the left-hand side, and only a few points on the right-hand side. So they have large importance values. So basically, the importance selects points that are important to the test domain. Then, so automatically, this weighting adjusts the solution, and statistical consistency is naturally guaranteed by this importance weighting. So then the question is, so how do we estimate the importance? Because this is unknown. And it's called importance weighting problem. And I was very much interested in this topic for more than 15 years ago. Then in classical approaches, so we had two-step approach. In the first step, we tried to estimate the importance function in some way. And we proposed several methods, and also other guys proposed many interesting methods. And one typical method is called least squares importance fitting. It's a simple least squares formulation to directly estimate the density ratio. And by that, so we can somehow obtain reasonably good estimate of the importance weight. Then, so using this R hat, so we solve an importance-weighted training problem. So now loss function is weighted by this R hat, then obtain the final predictor F hat. So this was the state of the art 10 years ago, and also we had a lot of applications in industry, and also in reinforcement learning, and also we did something on robot motor control. But we found that so this two-step approach is not really optimal because our hat contains some estimation error. So we spend a lot of time to improve the performance of our hat, but error cannot be 0 always. Then in the second step, this small error included in this R hat can be magnified arbitrarily in the second step because two steps are separated. So we should integrate these two steps and solve the problem directly. So that's the right way to solve the problem. And we were aware of that question 10 years ago, but we didn't have any answer at that moment. But finally, a couple of years ago, we had a nice systematic method to solve the problem. So we need some technical assumptions, but so in the end, we obtained a certain upper bound for the test risk. So to be precise, test risk squared divided by 2. So this is upper bounded by this J function. And interestingly, this J function is the sum of these two criteria. So and previously, we solved J1 first, and then so we solved J2. But now in our new proposal, so add them up, J1 plus J2, and minimize them together. So it's quite straightforward implementation, but we can guarantee that this is consistent. And we can also have a convergence analysis, convergence upper bound, convergence rate, and things like that. So this joint upper bound minimization actually works much better than the classical two-step approaches. So that was the research along covariate adaptation. Then more recently, so we are interested in so-called sequential shift. So far, we only considered training distribution, fixed test distribution. But if it's like change over time or changing environment, then maybe test distribution also changes over time. Maybe in real robotics, this should be natural. So now test 1, test 2 to test T, the distributions are changing over time. And in the last 2 years, we had papers on sequential label shift and sequential covariate shift. So label shift, only P of Y changes. So in classification, only class balance changes. So this is a kind of simplest distribution shift, but we had a very simple and systematic solution. Then last year, so we extended to covariate shift. So P of X changes over time. And these are quite theoretical papers, and they have very strong theoretical guarantee that so-called dynamic regret is minimized in some function class. So this means, so our solution, the risk of our solution and the risk of the optimal solution is small enough. And usually, so people analyze this kind of regret. So mean is taken over outside sigma. So this means they sum up all the risk over time and choose the the best solution, averaged over time. But this time, in our case, it's called dynamic regret. So mean is inside sigma. And so we always consider the best solution in each time step. But still, we can say that our solution is close enough to this best guy. That's actually a very strong theoretical guarantee. Okay, that was a good story so far, but still many unsolved issues and challenges here. And many distribution shift works focused on a particular shift type. Like in our case, we often consider covariate shift on the P of exchanges. So this is because it's easier to solve, to be honest, right? And nobody knows whether the covariate shift is really correct. In particular, so we just assume that we have unlabeled data from the test domain. Then basically there's no way to know whether the shift is really covariate shift, label shift, or whatever shift. We just assume it, and we just run some algorithm and see whether it works or not. So there's no really real guarantee in practice. Then another issue is the label noise. So as I said, input dependent noise is quite difficult to solve. But interestingly, this label noise can also be regarded as a distribution shift problem. Actually, P of y given x changes. So in the training phase, we are given noisy labels. So we have noisy output distribution, P of y given x. But in the test phase, we suppose we have clean labels, and we want to predict them. So then, so PTR and PTE are different. It is actually a distribution shift problem. So then, as I said, for input independent noise, we have a good theory. But for input dependent noise, so we only have heuristic solutions. Then, so let's forget everything, and why don't we solve this joint distribution shift problem? So now P of x and y changes between training and testing in an arbitrary way. So once we have a good solution to this problem, then all problems were solved at the same time. And also, we don't really need any assumptions. We don't have to know anything about the label noise, or we don't have to know anything about the shift type. So we just solve a joint shift problem. So that's our ultimate challenge here. Then already, so 2020, we had a simple method to solve joint distribution shift problem. But we need to assume that we have a small number of labeled test data or labeled validation data. So that's a difference from the previous setting. Then we perform stochastic gradient descent. And then for each mini batch, we try to estimate the importance weight. And importance weight estimation can be done by several different methods, but we prefer to use kernel mean matching. So it's one of the simplest methods. And we use the kernel mean matching in a slightly special way, and maybe the solution is not so reliable in practice, but this is just one step of stochastic gradient descent. So as long as we can find a reasonable direction to go down the slope, then so we repeat this process like thousands of times, or tens of thousands of times. So then in the end, we can obtain a reasonable solution. So that's the first method we had to solve the joint distribution problem. But this opened many new challenges. So importance weighting. So first of all, importance weighting requires the test domain to be included in the training domain. So this means, so we have PTE over PTR. So this means that PTR is not zero. So this means, so PTR has wider support like this, and PTE should be included in PTR. So there was a kind of implicit assumptions we made behind. And in the regression case, I showed a extrapolation problem, but that was not really an extrapolation actually, because the training distribution was actually Gaussian in that case. So we had Gaussian tail even in the test area. So the density was not zero. So it was not a pure extrapolation. But in reality, we want to handle extrapolation out of training domain test data like this. So this is a challenge. But last year, we had a nice practical method to solve this problem by identifying this point. By this point, we can split the test data into the training part and pure test part. Actually, we can utilize outlier detection method to identify this point. So we used one-class support vector machine in our paper. Then, so we can actually handle this problem properly. But still, like for joint shift problem, so as I said in the previous page, we are assuming that we are given label test data. And this is a very strong assumption in practice, because usually we don't have test data, labels from the test domain. So then, so we are wondering whether we can combine our weakly supervised learning theory in this framework. So we don't expect to have like pure label data from test domain, but we may assume that we can obtain weak labels from the test domain. So if we don't have any label from the test domain, then we can't really solve the joint shift problem. So we have no information about the test domain. So we need some supervision from the test domain. And in our earlier paper, we just assumed that we have strong labels from the test domain, but this is too strong in reality. So as a compromise, hopefully we can have a similar theory for weakly supervised learning and try to have a joint distribution shift problem. Then finally, we want to combine everything and extend it to continuous sequential joint shift, so over time. Then, so it's a kind of extension of continual learning to like changing distribution. So nowadays in the machine learning community, continual learning is quite popular. Like one learning system is lifelong learning, performing lifelong learning for many different tasks. But naturally, over time, so distributions are changing. We need to explicitly handle like distribution shift in the context of continuous learning. But still, that line of research is missing. So we hope like this line of approach is suitable for tackling continual learning. And our ultimate challenge is to have machine learning with least assumptions. So that's our ultimate goal. Because so far, so we consider some specific problem setting with some assumptions. Then try to develop like a strong algorithm that gives the best performance. But in reality, in many cases, we don't really know about the assumptions of the problem. In particular, when we try to solve a new problem, usually we have no knowledge. We just have small number of samples made by like engineers around or something like that. So then, so what we want is to have a fairly general machine learning technique that has like minimum guarantee. Like if you have a strong assumption, then we can give a strong solution. But if this assumption is violated, then nothing is guaranteed. So that's the biggest problem nowadays. But once we have a very simple and flexible method that can be applied to a wide range of problems with some minimum guarantee, then that should be the first method we should recommend to use in practice. Maybe such a method, machine learning method with least assumptions, maybe not so strong. Maybe the performance is not so good, but at least we can guarantee that it's safe to use this technology because we try to have a minimum guarantee. Then once we are sure that, okay, the current problem is suitable for machine learning, then it's time to convince our boss to provide more funding or ask more collaborators to join the project and know more about the problem. So initially, so we have no funding, no data, less data, but still we want to identify whether machine learning is really useful or not. So having a machine learning technique with least assumptions is really necessary, and this is something we are currently tackling. And hope that like along this line or maybe another problems, we can find an opportunity to collaborate with IIT. So that's why we wanted to have a workshop like this. So hope that these 2 days will be quite fruitful for all of us. Okay, thank you very much.
Thank you for the presentation. Are there any questions?
Thank you very much. This problem of the distributions of the training and test sets in robotics has been also addressed in the past, and some solutions that have been proposed is to use basis functions that are inspired by the physics of the robot. so that you can get better generalization because the basis functions are preventing you from overfitting intrinsically. Is this something that you've been looking at, maybe with ways of proposing, exploring the functions that you use for the approximation or the selection of the hyperparameters of the learning solution that you use?
Yeah, so thank you very much for the nice comment. So there must be many different approaches, and maybe typical one is consider a model of changing distribution. Like in the case of robotics, maybe you have some like physical model behind. Then somehow you can model the change between training and testing, and try to explicitly handle that changing distribution. So that's one way to tackle the problem. Then our case is more like kind of non-parametric. We don't really assume any specific change. So, okay, we say it's covariate shift, but we don't say more than that. So how distribution is changed is not really specified here, but we can cope with any change in that framework. But these two are, of course, naturally related. And if you have some additional knowledge on the changing distribution, we should definitely take that knowledge into account. Then, so I think all the methods can be improved in a natural way. But then there's another risk that this model is, what happens if this model is wrong? So we have some physical model, but it's not always perfectly correct. Right? Then our solution will be biased. And then we need another method to reduce the bias. And this is another important challenge. Maybe combining these two approaches would be quite important in practice. Thank you very much.
Great. Another question? Here, Vittorio.
Thank you, Masashi. Great
Thank
talk.
you.
I'm actually really interested in this kind because what I call the learning with imperfect data, and this is actually what you are in a way explaining.
Oh, great.
Today.
Already you have a solution.
No. Solution, I don't know, it's far away. Because as you show also, there is a lot of imperfection you have to deal with, and noisy labels, supervised. So another way to do this transfer between the data and it's regarding the fact that how to transfer the tasks instead of the data. Mm-hmm. Are you working also in this kind of work?
So task means?
Task means that you don't need, so now you have transfer learning, you have this shift of distributions. Maybe you don't have to learn anyway from segmentation task how to do detection, all this kind of stuff, which is actually another way to do transfer learning in a way.
Right. So our case, still we are solving the same task, but having different distributions.
Different distribution shifts.
But more, if we generalize the problem more, then right, it's natural to consider different tasks.
Yeah. It's even more general, yes.
And as long as you can relate these two different tasks in some way, then you can somehow transfer knowledge from one task to another task. Maybe this also depends on the knowledge you have. If this knowledge is perfectly correct, then this transfer should be working well. But if our knowledge is somewhat noisy, then this transfer can cause some additional bias. We need to correct the solution further. Maybe that part is still open.
Maybe another quick question, or otherwise we go for the next.
I can have it another one.
Oh yeah.
So what about so when you're talking about the distribution shifts, so in my experience, depends how much shift you have to consider. In your experience, so what you can say about the fact that there are specific application in which the shift is closed, so you can in a way try to solve it, in other which is very large and it's more difficult?
Right, so like for this simple case, so this setting is really tuned carefully. If two distributions are closer, then problem is quite easy to solve. And if two distributions are slightly more far apart, then none of the method works well. So, right, so we need a reasonable overlap between two distributions. Otherwise, we can solve the problem. Then, so for that situation, so this method, so we had last year, this is a kind of real extrapolation method, but we need labels from the test domain. That's an additional.
Which is a strong assumption. Yeah. Thank you very much.
Thank you. That's the essential question.
Again.
First of all, many thanks for organizing this. I think it was, yeah, we had another one many years ago. I think, do you remember? 19. So it took a while to organize the second one, but for obvious reasons. But I'm glad to be here, to be able to continue this series of workshops, and also hope an excuse for further collaborations. I think we may benefit also from what you're doing, and you know, I think we have similar problems that we'd like to address. I'm going to be talking about IIT, and specifically January 1st, 2024, we actually launched a new strategic plan that, as you're going to see, is trying to give a push to AI and machine learning applied to the various research domains of IIT. So not only robotics, as you saw today, but also to the other disciplines that we study. So we apply it to physics, to chemistry, to biology, and so forth, because it is becoming very fundamental to use data, not to throw away the results of our experiments. We still remain experimentalists, but we have to use this plethora of data that we collect in every day from our machines, from our instruments. Okay, yeah, this is just my name. Short history about IIT. We're not as old as RIKEN. IIT was only created in 2003, so last year actually we celebrated our 20th anniversary, so it's a short life, but I think a successful one so far. And the other aspect that I think is important is that we also have to collaborate with universities, because we don't have students ourselves. It's only through universities that we get the students. So for this reason, IIT has a geographical, a bit like RIKEN, geographical extension across Italy in order to be able to be close enough to universities we would like to work with. The goals of IIT are both research and also, this may be important, I don't know if you have the same goal, but also we have a mission to have an impact on the national industrial sector. So try to do something that can be taken by companies, which doesn't mean to be always very applied, but it means to at least think of potential applications, not to be completely disconnected from potential applications. About the size of IIT, at the moment we're managing 18 buildings across Italy. The headquarters is Genoa, which means most people are actually located in Genoa, but all the dots there are centers of IIT, typically small and often hosted by universities, but not always. Sometimes we're managing our own space, our own laboratories in different cities. Just to have an idea about the size of IIT, last year, the, let's say, preliminary balance when I wrote this slide was about 160 million euros. Ended up being 163, I think, when we finalized the numbers, but roughly this tells you what is the size of IIT. At the moment, the other important aspect is we have a good contribution from external projects. So it's about, I think of those 50 millions is 40 something from the EU and from standard funding agencies, and 15 millions from companies. So these are the rough numbers. The size of the labs, this is the plot that shows that we basically 2,000 people overall. And so there was a growth, and then we reached a sort of steady state now, which is what we can pay from the yearly budget of IIT. The other, let's say, important aspect, of course, is science. robotics you saw. The other topics that we are developing are nanomaterials, life technologies, life science technologies, and computation. Computation, of course, includes machine learning and AI, but also simulations, and we have a good chunk of people doing atomistic and molecular simulations, which is a big topic for material science, but also for biology, studying, I don't know, biomolecular interactions and drug discovery. We'll see something later. The other important message that I wanted to convey is that our disciplines are working together. We don't care much about subdivisions. Teams can be interdisciplinary, and we tend to favor, for instance, applications of computation or machine learning to the various disciplines. Alessio is formally, for instance, a computational person, but is working a lot with robotics almost every day. So it's not, we tend not to separate things. We have people doing, for instance, synthetic biology that are working at combining control theory with biology. That's something that is fairly typical at IIT. And there are other topics that are equally mixed, as I try to represent with this plot. The other important aspect is investing on people. As you may know, I don't know here in Japan, but it's becoming harder and harder to find good people and find them in large quantities, especially because we're not a university. You know, finding students for us is more difficult. We don't teach, not to large enough extent to gather new students. So I think it's always a struggle to get people. But over the years, IIT managed to get enough international, as is shown here, 31%, enough Italians coming after they spend some time abroad. We have some fiscal incentives for people that come back to Italy, and which means that we can precisely count how many are actually benefiting from the incentives, and 21% of our population. And then, of course, because we're based in Italy, about half of the researchers and technicians are actually Italians. And here are the numbers. I mean, yeah, they are what they are. They keep changing as people also change. The other big investment we've done is in infrastructure. We have an HPC, a machine of about 3 petaflop, decent enough. I mean, can't probably compete with big, large machines, but it's okay because it's ours. So it's fully accessible. We're managing the machine. We have people hacking the operating system, and we have people that can develop software for that machine. So it's not just a service. It's more than that. It's some know-how that we internalizing because we have the hardware. And similarly for genomics and also nanomaterials. I mean, these days you may think that doing genomics actually is just a matter of finding someone that can do the sequencing for a fee. But actually what we're doing is trying to learn something how, for instance, to use the machine, whether we can exploit some of the peculiarities of some of the machines. So we experimenting with third generation whole genome sequencing, which is nice stuff that requires further software development and improvement of the procedures and so forth. So I think there's a value of the investment in infrastructure that we carried out in the past years. And we now have allocated about a bit less than 40 million euros in the next few years for additional improvement of the laboratories. Partially also to renovate some of the labs that are, machines get old, so you need to keep up and maintain them at the best possible level. And now going to the strategic plan that started in 2024, you know, nothing easier than start with an image generated by whatever, Dali, I think this one. I simply put some of the keywords of the strategic plan, and this is what I got. So I think it's kind of interesting. Anyway, the main motivation why AI is becoming very important, well, of course, you can guess it. I don't think I have to justify this here to this audience. But normally what I say is that, you know, it's becoming one important, or probably the most important use case for AI is science itself. So, and this is Eric Schmidt, but the other day, the European Commissioner Verstager say the same thing. If we're going to invest in AI, and they were promoting some new investment by the European Commission, probably the application to science is the best use case that we can find right now. Because we can accelerate science, we can accelerate innovation, we can find new solutions to various problems, and exactly because we have data-driven models that we can apply. And of course, I mean, if we, again, because we're citing people, Edward Teller, you may know the name from Oppenheimer, from the movie, actually, because he was one of these controversial characters, and he was controversial. But this sentence, I think, is nice. The science of today is the technology of tomorrow. So, I mean, if IIT has to fulfill the mission of delivering to the industrial, let's say, milieu of the country, then why not investing into basic science so that we have something to transfer to the companies? And what are the big high-level challenges where we may want to invest? Maybe it's easy to say. Italy, like many other countries, is becoming old, and therefore healthcare has a cost, and a cost that is increasing. And also the workforce is shrinking, so the robots are needed. So it's not, and this is a paper, recent paper from the Lancet that compares 2021 to 2100. So, and what happens is that basically worldwide, you see a flattening of the fertility rate, which means that our population will be smaller. And for Italy, if you do the calculations, means that we're gonna be missing 3.7 million workers by 2040. Simply people that retire and hopefully are enjoying pension, if there are robots that are working for us and producing what we had to produce. So this is one number. The other thing that is important is clearly the climate change issue, where technology, again, can be fundamental. So this is, again, the other high-level thought that we had in designing a strategic plan. We like to, our robotics, our nanomaterials, our life science technologies, to our AI to be addressing these two problems: healthcare on one side and climate change on the other, sustainability in general. I'll give you an example because I think it's a nice one, is easily explained. This drug repurposing via simulations. So basically, and this become, it's a startup launched by two of our PIs. The story is nice because one of the PIs, a young lady, was working on neurodevelopmental disorders, and in particular, a known drug that is called bumetanide, which is works well to regulate the level of chloride in neurons, but unfortunately has side effects. So the same molecule binds to an isoform of the protein in the neurons. In the neurons is a channel, but the same channel, unfortunately, in the kidneys, make the drug a diuretic. So eventually, the dosage that is needed for the brain is not good for the kidneys. So the thing is, how can we repurpose this drug if it has so much of a side effect? So what they've done was basically to create models, models of the drug, models of the proteins, and start screening in such a way to find out of a large database of potential similar molecules, find some of them that had an effect on the protein in the neurons, but not in the kidneys. And they found 2 candidates, they patented them, and they went for launching company because they like to go, after the first animal studies, they like to go in humans and go for clinical trials. So they needed money to start this process that is very long and very expensive. But what is important, I think, is that all this stuff happened in maybe a couple of months of experimenting, refining the models, trying to figure out what was wrong in the software. Anyway, the usual stuff, but it happened very quickly. While normally, if you had to do the chemistry for every single molecule, would have taken forever. They screened 135,000 different potential candidates. So this is a large enough number. So I think this is a good example how AI on one side, the ability to build sophisticated models of, in this case, proteins and other small molecules, can change the way we do science, can make it faster, more efficient, less expensive, and so forth. So we like to build a strategic plan exactly on these elements. The structure we devised is a bit articulated. Bear with me for a moment. We basically have the research domains, robotics, nanomaterials, life science technologies, as I mentioned earlier. And then we wanted to combine those in such a way that our PIs work together towards high-level objectives, grand projects. And we invented 5 of them. One is on sustainability. And these were completely bottom-up. So our people, our researchers, actually also with me, we met for about a year discussing potential. We do this, we do that, how do we do it, what is the organization of these projects, and so forth. And now we came out with 5 of them. One is sustainability. Another one is called brain and machines. That is very relevant with what we're discussing today. The idea is to gather our knowledge about neuroscience, our researchers that are working in neuroscience, and potentially get closer to what we're doing. A 2-way project, because also the neuroscientists need machine learning to model their data. We have now beautiful technologies to record from hundreds and hundreds of thousands of neurons simultaneously, and so it's a lot of data that needs to be analyzed. And then we have a program of machine learning where our theory people, but also Alessio and others, are combining physics and machine learning. So physics informed machine learning. Daniele perhaps mentioned some of that. Also, that's something we care about. We have a program on RNA, not because it's very well known these days after COVID. It is something we started in 2017, so it was well before COVID, but because it's very interesting, and it's a chunk of biology where there are large opportunities for developing new drugs, and not for viruses per se, new drugs in general. And last but not least, the last big program is called Technologies for Healthy Living. And this is where we have all the robotics applied, for instance, to rehabilitation, exoskeletons, prosthetics, and so forth. But also, we're developing technologies for measuring the health status or the health or the not so healthy status of a person, so the physiological levels of various parameters and so forth. What else? And then we have everything that doesn't fit into these 5 programs is called Blue Sky Research. And this is a commitment of IIT to stay also in the business of doing basic research, because otherwise there's no point in discussing just technology transfer. If we don't have anything to transfer, what is technology transfer for? We're investing, so the entire budget of this, it's about €1 billion in 6 years. And there are various components. The green one is what we receive from the state. So it's sort of guaranteed, fingers crossed. Let's keep our fingers crossed. It's sort of guaranteed. Some of the money in blue is devoted to new infrastructure. We invest in capital fund. So basically our endowment, it's not technically, it's not called endowment, but it doesn't matter. It's money that it's already, let's say, in the bank account of IIT, so we can spend it, and it's going to go in infrastructure. Competitive funds is estimated to be roughly what we have now. We thought of 4% growth in the coming years. Well, if we manage, it's good, otherwise it's gonna be a bit less. And also the brownish top part is the contribution from the Italian Recovery Fund. Is some investment that happened through the European Commission. It's called Next Generation EU program. Gave us about 120 million that is spread up down to 2026. It's going to contribute to the total budget of IIT. So this is the situation. I think overall there's a happy situation. I mean, I don't think we have an issue with money. But of course, has to be spent well, and it's a big change. We have to think of acquire data, store data, use data well, develop new machine learning algorithms, and of course, carry out our research. This is something that we started. Also, it's luckily we got immediately an ERC grant to support a new laboratory for chemistry. It's a completely robotized laboratory. There was a project that allowed sort of to understand the problem. So it wasn't enough money to build the laboratory, but it was enough to understand the problem. We got the ERC grant. IIT is investing 7.5 million on a creation of a fully robotized lab for chemistry. This will allow both to use machine learning to invent new experiments. Let's call it invent, but you know, with some hints from our researchers where to go, then use machine learning also to design the experiment, execute the experiment in a lab that is very efficient and it's completely robotized, do the measurements, the characterization of the materials, take the data and maybe feed the data back into the model, therefore improving on the machine learning and the capacity to predict correctly, given what we want, what is the chemistry that allows to get there. And these are examples that I've taken from the internet, but just to give an idea of the complexity of the problem. This is a paper on Nature Communication. It's not a super new one, but there are hints on what is the complexity. Estimations are that drug-like molecules is probably a space of 10 to the 60 possible molecules. Unfortunately, the good ones are few into this enormous space, so finding them is not easy. But there are methods, and these are, I mean, they were working well enough in 2020. I'm pretty sure we can do better also now, today. And I don't want to say much more, but it's just the idea that you can try to engineer a drug. So instead of just screening, as we've done before in the example they showed earlier, that you can engineer a drug to obtain certain function. So in the paper, in fact, They have a certain genetic profile from cells, and they're trying to figure out what is a small molecule that obtain that genetic profile. The genetic profile can be silencing a gene or activating a gene that wasn't active or something like that. So the target is having cells that respond to that molecule. And then they use, generative adversarial network in that case, but it's just one example. And actually IBM has a system that does something called retrosynthesis, which exactly tries to figure out, if I want to obtain this, what is the path that leads from basic components to the particular molecule that I like to build. And this, again, I think interesting. It's an active possible field of application for AI. Let me go on further into examples. I spoke about blue sky research, and these are examples the Robotics lab already mentioned. This is another example of type of materials that we study. There are a class of materials called perovskites. They're used. They're very well known now for solar cells. They reach a performance level and an efficiency level that is comparable to silicon. The advantage is that if you don't have silicon, you can replace with something else. And but they can be used also for other. For instance, one solution is for building scintillators, and a reason why you may want to build a scintillator is, for instance, for detecting radioactivity, and you can build large panels that are sensitive to radiation, and that's one example. But there are solutions also for basic physics or for PET scan machines. So these are potential applications of these materials. And this is a class of materials that are being studied. And as I say, this mostly curiosity-driven research that our material science people are carrying out. So an example of the variety of potential, let's say, solutions that we're gonna be studying at IIT. The other, I mentioned the 5 flagship programs. One is the first one, Technology for Sustainability. There are a couple of examples of what we're doing here. We're doing, for instance, robots for agriculture. This is potential applications for robotics. And here there's robot, for instance, automatically trying for now to prune vineyards, which is a very high value-added production, at least in Italy, for wine, clearly. And other applications are material-based. We're designing, it's an interesting result of the European projects with designing materials that in case they interact with pollutants, they become, or they activate fluorescence. And so you can, and they're biodegradable themselves. So you can just spread them across fields. And in case they become fluorescent, you can send a drone with a camera to check it out and figure out whether the particular field does, and what level of pollution is in that particular field. Couple of things. And then last but not least, this is, again, a startup company that has been launched by IIT, and it's a company that is working on biodegradable, compostable materials. So the materials made of cellulose that has been recovered either from paper or from food waste, so from vegetables. And they are, cellulose is recovered and treated using chemistry that is entirely green, so it's water-based. All the solvents are water-based, which means that they don't pollute on top of, they just recover, but don't pollute on top of that. And these are some the topics, as I mentioned, that are happening in the technology for sustainability. Moving to brain machines, we have two components. As I said, there's the neuroscience. That's an example of the type of recording you get and the credible resolution of the activation of neurons in large enough neural networks through technique called optogenetics, where you basically genetically modify neurons to be sensitive and to light, so you can stimulate and also record from neurons. You get images like that one, and this is clearly a large amount of data that have to be studied. And the other example here is an application of, let's say, I don't know how to call it, but it's a training of children diagnosed with autistic spectrum disorders through an interaction with our human robots. And there's some results there that are clinical testing, pre and post interaction with the robot, doing certain tasks that are very stereotyped and prepared exactly to teach certain skills to the kids, are actually effective and show, in this case, extremely good results, and also compared to the case where the teacher is just a human, the robot does better, scores better, and et cetera, et cetera. There are all the cross checks and controls to verify that this is actually the case and it's happening. Moving to some of the computational and part of the teaching science to computers flagship. This is an example of the development of catalysis for production of ammonia. Ammonia is one of the components of the fertilizers, so it's very important because you see the number there. 5% of the natural gas and 2% of the energy production, 5% of the global CO2 emissions are due to the production of ammonia, and this is needed for agriculture, and clearly agriculture is needed because we have to eat. Therefore, having an impact on the efficiency of the process of production of ammonia has a huge impact on the CO2 emissions. So this is an important problem, and unfortunately, there are, in theory, processes that work better than the industrial standard, but the theory doesn't translate into the applications. It's very difficult, and what we do, and we actually go into the production plants and try to understand how to make a simple, the chemistry into an industrial production. That is a slightly different problem. And this is there's a lot of machine learning being applied there, either to approximate functions that are part of the, I don't know, the electron distribution in the material, or you name it, that are nowadays done from data produced by simulations that are too expensive to be carried out, can be only carried out to collect data for training the neural networks. So it's a lot more efficient to use neural networks rather than the original integration of differential equations, whatever it is. So therefore, that's a direction that we're following. Also here, there are a couple of, let's say, keywords of the type of research that we like to do within these flagship programs. Includes physics-informed machine learning, continual learning, large scale, and there are a number of items there. There's more, of course, and I think Vittorio and Daniel and Alessio can complete the list later. Talking about RNA, since time is, I think, getting slowly to an end, I'd like to give you another example, because this, I think, is super fascinating, and it, I think, is getting really to the point where we can engineer molecules to obtain a certain effect. This is entirely software-based, although this is an experiment eventually, but it's entirely software-based, which means that some of our people develop software to figure out a sequence of a short RNA, an RNA aptamer that binds specifically to a certain pocket in a protein, and they can engineer it. It's not a screening process anymore. It's letter by letter, the sequence that determines a certain function for that piece of RNA to bind to that protein. So if you know the process that you like to drug, then you can try intervening with an RNA molecule. Now, this is a theory, and it works very well in vitro. Then delivering is a different thing. So it's not that we can solve all possible, disorders just by knowing this, but it's the first step. It's super interesting. What you see here is microscopy of one of these RNAs that binds a certain protein that is forms aggregates in ALS. So ALS is a neurodegenerative disease, and one of the causes is probably a misfolding of proteins that tend to aggregate. Some of our biologists believe there are certain RNAs that are the basic attaching point for these proteins to aggregate. The aggregation basically limits the capacity of the neurons to activate, and eventually they also die. So for this reason, the disorder is neurodegenerative eventually. Now, what we've shown is that we can design an RNA that disaggregate the aggregates, at least in the in vitro works. And then theoretically, you can target other things. Another molecule that is very well known, you may know the gene called BRCA2 is related to breast cancer. So also that one gets into the nucleus of the cancer cells through a transporter. And also in that case, you can design an RNA that influences the transporter, and the transporter cannot bind to the the BRCA2 protein. Therefore, again, there's a possibility to intervene in processes in cases where they're misfunctioning, and this is all possibilities that we can study through software, basically. And so far, what we determined through software with a bunch of adjustments turned out to be okay also in vitro. So the effect is there. So this is becoming accurate enough. I'm going to finish very quickly. This is some of the robotics applied to the rehabilitation or prosthetics. I think this, it's interesting for the social value. I think seeing a young guy jumping and running while trying one of the devices, and this was the first trial, by the way. I don't know, now I can probably run 100 meters faster than whatever. But the other thing that is important is there's a control and bit of machine learning also there to be used for the controllers, because the interface is non-invasive, and it's kind of the control signals are low dimensionality, but you have to reconstruct complex movements. And so you have to try to infer from these signals enough to be able to generate natural movements. And this is what we're trying to achieve here. So we train neural networks to the pattern of the activation of the residual muscles at the amputation level, and we try to transform them into the correct movements, as you can see here. Also, the ankle device, although it may seem simple, is a real robot. There's a motor there that activates, pushes, we're designing it in such a way that you can climb stairs, so you don't have to drag your prosthesis upstairs. The prosthesis is active and pushes upstairs. So this some of them are, let's say, devices that we're developing. Of course, there's more, and the idea is basically here to eventually develop enough of these machines to measure and support, as we say, the elderly population. That is going to be the case in Italy, and I think it applies also to Japan, or applies worldwide, probably. Okay, I think I'll stop here. I have 50 more slides, but I don't think I have time for those. Thank you very much.
Thank you, Giorgio. And are there any questions? Ah, Masashi.
Thanks for the great talk. So it's a great overview of the entire IIT. So I think in many projects, AI and machine learning are really involved. And we have a similar situation in RIKEN. And I'm on the AI side. Then in other projects, they all need machine learning and AI. Yeah. But we are more like researchers, and we are not really engineers. So then there's a kind of gap between their side and our side. So in IIT, so are there similar problems, and how do you cope with this situation?
To a certain extent, yes, because sometimes you have the super theory person. It's difficult to put together with the engineer. But it's not so bad, meaning that I think we have enough people that can kind of connect the two domains. And the reason is that we probably are, many of them are in the same building, so they can talk to each other. And these programs that we launched are actually organizing, recurrent meetings. So there's enough crosstalk between the engineers and the, let's say, theory, more discovery part. So I think of course we always have to push people to do it, but I think it's gonna happen. Also because the quality of data that we're getting from our experiments, I think at this point it's so beautiful that even people that are developing algorithms will have a use for that type of data. I mean, Daniele showed this teleoperated robot. This best possible case for acquiring enormous amount of data in very complicated scenarios and train models and trying to build autonomous controllers for the robots. So I'm an optimist.
That's great. Thank you.
Okay, great. Wow, one question there.
I have microphone here.
Ah, okay.
So in one of your slides, you mentioned a startup. So do you somehow promote startup application of your output, or does it just happen?
No, we do. We try to do it actively. There's a division of IIT for technology transfer. It's about 15 people helping. Yeah, it's an active process. Although I must say that very often our researchers become passionate about creating a startup, because it's, in many cases becomes, it's a kind of a dream. You have something that works and you like to, I don't know, I think there's a beauty in science, but there's also beauty in creating a startup. And then many scientists come back. It's not that they disappear. We lost a few, I must say, because they're now in the business, they're minding their business. But in general, I think it works well. And also for young people, it's a good opportunity. It's a good experience, I would say.
Okay, great, thank you.
So thanks again, Giorgio.
Thank you.
Thank you for your introduction. Today I wrote or developed robot as well, so maybe I will show demonstration later. And so today's talk is on robotics and AI for cognitive health. And so this is Mihoko, team leader of cognitive behavioral assistive technology team. and then RIKEN AIP. The number of people with dementia is rising rapidly, particularly due to worldwide aging populations, particularly in low and middle income countries. So mastering the challenge associated with aged societies in general and those associated with age-related brain disabilities is therefore of critical global importance. And so the name of the team, Cognitive Behavior Assistive Technology, is a new term which we named when I arrived in AIP. And so existing term was Cognitive Behavior Therapy and Assistive Technology. And combining these terms, we developed, we named Cognitive Behavior Assistive Technology. And so this is a technology which assists cognitively and behaviorally ideal lifestyles. And research question is, how can we maintain our cognitive functions until the very end of life? So in Japan, there people are super aged people. Numbers are really growing, and so dementia is not a kind of rare but really common disease for us. And maybe Italian people also live very long. And have you, is your family or grandmother and grandfather have dementia? Oh, too, yeah. And so my grandmother was also dementia, and I got very interested in that. So maintaining intelligence of our health, our selves, rather than machine or robots to be intelligent. And so this is more, well, crucial, I thought. And so we really focusing on conversation because embodies in intelligence is demonstrated in conversation, since thoughts and feelings are exchanged through visual, auditory, and motor functions. And multiple cognitive functions such as memory, comprehension, reasoning, and executive functions are utilized in conjunction with bodily functions. So based on these characteristics of conversation, we are developing technology to intervene in and to help maintaining and improving the cognitive functions of older adults through conversation. So today we present the effects of group conversations among humans using a moderator robot on human cognitive functions and the cognitive functions that can be predicted from conversational features. For moderating group conversations, we developed this robot. So this is for moderating group conversations, and the robot is in front of the people, and then people are sitting surrounding this robot and then moderate conversation with this robot. And so this is another type of robot for dialogue intervention that not only talking to human and human, but rather robot and human. And so we ask questions to the robot and to maintain our cognitive functions, because asking questions is one of the most demanding cognitive tasks. And so people with dementia cannot ask questions. So asking questions seems it's not a kind of high. For people with normal cognitive functions, we do not have so much difficulty in listening to the story and asking questions according to the story. But once we lose our cognitive functions, and it has become very difficult. So doing the kind of cognitive task which may not be able to do after decline to maintain the functioning is our mechanism for intervention. And so based on the idea, we did work on cognitive intervention through photo-integrated conversation moderated by robots. We named PICMORE program, and we did a randomized control trial. And so a PICMORE program, participants prepare taking photos according to the themes. And so participants are assigned themes a week. So, and there are 12-week program. And so, for example, the next week we will talk about favorite things, and for example, and then participants take photos of favorite things. And then at the same conversation session, the photos are displayed on the screen, one after the other. and give a talk one after the other, and then asking questions to each of the talks. And so the photos are shown. And then soon, and after the conversation session, we do immediate recall of the photos. And so who provided each photos, and the photos are randomly shown on the screen. And so time management, each person has 2 photos for each themes, and then 1 minute for each photo. And so 2 photos, and then 2 minutes for talk and listening. So if there are a group of 4 people, and then 6 minutes for listening to other people's talk, and then answer to questions of each photos for 4 minutes, and asking questions to other people's talk for 12 minutes. So in this way, we can manage the conversation quantitatively. So rather than, so usually we do chatting, but without any constraints or rules, and we cannot estimate how much we ask, or how much we listen, or how much give a talk. But in this way, we can do intervention, quantitative intervention. And taking assistance based on the amount of speech by a robot is also done during question and answer session. So people who ask questions less, and the robot asks such people that is there any questions? And then so each person really definitely ask questions to each talk. And we can control quality and quantity of intervention. And so this is a sort for diagram of randomized control trial. And so we did intervention using PICMOR program, and control group, just group conversation without any rules. And we found that verbal fluency improved for only intervention group. And so verbal fluency is one of the cognitive functions which decline as people ages, and dramatically decline when people have dementia. By improving the verbal fluency, we can extend the time to lower the threshold of maintaining a kind of social life. If cognitive decline like this, and then the starting point of the cognitive function is higher, and then the time to lower the threshold will be extended in the future. And we did also MRI studies on the effects of PICMOR and resting state functional connectivity, and voxel-based morphometry, and track-based spatial statistic analysis of diffusion tensor imaging. These are 3 major analysis methods for MRI, and we found that positive effects on people who attended intervention program. And we also found scaling laws in natural conversations among elderly people. And we recorded large-scale data of 1 million words from group conversation among healthy adults through RCT, and analyzed the relationship between spoken language and cognitive functions. And we found that word pattern followed the scaling laws, namely Heaps' law, is respective of cognitive function, and that the variations in fixed exponents are associated with cognitive function. So people have large vocabularies. So the x-axis is a number of words used during the conversation, and y-axis is the types of words or kinds of words. So people who have larger vocabulary do not saturate while they are talking, and so they talk more and more utterances, and then give words, and then the kinds and numbers of words or a kind of types of words increases. So the Heaps exponents is larger for people with larger vocabulary. And results suggest that we can predict the cognitive functions of speaker through analyzing transcribed conversation data. And also, we found the time orientation of older adults in group conversation, and so it's associated with memory functioning. And so utterances in group conversation were classified in terms of time and experience and knowledge. And recent tag was also added to distinguish between recent and remote memories. And logical memories were associated with frequency of utterances that mixed past experience and knowledge, and those about recent knowledge. So people talk about recent topics tend to have higher memory functions, which means that in order to talk about recent things, we need to memorize something in recently and then maintain the memory and then recall that topic at the time of conversation. But many people, older adults, talk about past experiences, and then when they talk about past things, they only remember, and then we cannot see whether the person can newly remember, new or encoding functioning. But if we talk about recent topics, which means that we can encode something and to so memorize in our brain and then recall soon after. And so we can see the hippocampal campus functioning, we can estimate through conversational data. So findings is that conversations may potentially serve as cognitive intervention if the condition met, since one speech is an output of brain as well as other speech is an input of one's brain. And actually we found that verbal fluency improved for doing such a kind of, input and output are done one after the other in a well-organized manner. In terms of prediction, speech in conversations may also predict cognitive decline, since one speech is an output of brain. So vocabulary richness and time orientation of speech reflects memory or cognitive functioning we found. So not only measuring MRI instruments, we can just observe conversation, and then we can estimate the internal state of brain function and brain and structure and functioning. We can estimate. And so based on, this is a result of face-to-face conversation, but during COVID pandemic, we could not do such experiment. And so during that time, we did developed kind of application of dialogue system, as well as remote communication system. And then we did also experiments using these systems. And so without meeting older adults or gathering older adults, we could safely do the experiments, and so evaluated the effects of communication, well-organized communication, and so it affects on cognitive functioning. So this is a robot which assists turn-taking. And so people who speak less are asked to ask questions. So this robot did this role. And so sometimes it's difficult for human moderators to stop or to prompt people to talk. But the robot can do so without any hesitation. And so this is a dialogue robot for cognitive training. And the robot gives a talk, and older adults ask questions, and the robot answers. Because listening to other people's talk carefully and ask questions is one of the most demanding tasks, cognitive tasks. And so it's very difficult for people with cognitive decline. So we designed this system at first and then tested with healthy older adults. So this is the system. And then, do you like to start talking? And yes, say yes.
The 20th of May 2024 now. We will begin the Koimajin method. The theme will be healthy and careful. When I reached retirement, my child bought a bicycle.
So this
It
robot
feels
talks.
good to run by bicycle on a sunny
So
day.
this is a picture of
At
bicycle.
first I couldn't go far. But I got used to it little by little. When I went to the next city, it was easy to go. But on the way home, it was hard because the pedal was not so good. Even now, when you look at the cats, you are around the nearby towns and rivers. The knees are not overwhelmed. The amount of exercise is large. And it is the best for a change. Now, please ask a question.
So this is a story that originally this talk was provided by real-world adults through group conversation, and we collected some of the stories and then we implemented into the robot. So this robot stands for real-world adults. And then so the person is retired and his children give a gift of the bicycle. And then so as a gift, and then he started riding a bicycle. And then so he do some exercise and about 20 kilometers a day, for example. And then so we can ask questions to the robot based on this story. So it's now counting down. So it's for one story, and we set 4 minutes for asking questions. And then so older adults ask questions, about 8 to 10 questions for 4 minutes. And then when I ask questions to the robot, and the robot answers to this story. So maybe I can ask. How frequent do you ride a bicycle?
Riding a bicycle is not difficult for me. I enjoy cycling and find it quite relaxing and enjoyable.
Maybe he doesn't understand so much. Yeah, excuse me. So, but so sometimes the robot cannot answer it properly, but anyway, I may ask another question, one after the other, and sometimes it answers better. Answer. Anyway, so recently translated this system into English. Yeah, and so for experiments, we developed a Japanese version, but for demonstration and also maybe future experimental purposes, we did a kind of multilingual version. And actually, we have also German translated version as well, and hopefully Italian version translated from Italian version maybe. Yeah. So this is the ongoing system. So this is an interdisciplinary cognitive behavior assistive technology team. And there are 3 subgroups and developing conversation supportive system like this and this. And another team so developed analysis method. And then so Tomek, the next speaker of today's workshop, he's developing analysis method using EEG data. And another subgroup doing evaluation of the effects of the usage of the developed system and using the analysis method we develop as well. And our so team members' background is really diverse: mathematical biology and sociology, software engineering, cognitive neuroscience, neurotechnology, public health, human-computer interaction, biomedical engineering, and robotics and AI. And so our team is also diverse. So we took a picture in here. And then so females are 1/3 and age range from 20s to 80s. And countries coming from Poland, Canada, Thailand, and Japan. And another work, so it will be given by Tomek for the next talk, and machine learning approach for early onset dementia neurobiomarker using EEG network topology features. So through analysis of the EEG data, we can also predict cognitive decline of older adults. And so such technology is also needed. And so
thank you for your question.
Oh, so 4 minutes.
Start screening.
Yeah. So I may
Please choose the
return.
topic.
Okay, I return to the original page. Yeah, so he was waiting for my questions for 4 minutes, and then it's 4 minutes. So he's now said, thank you for asking questions. And to summarize, we have succeeded in developing novel technologies which enable cognitive intervention through social activities in order adults with evidence. This is a word for first evidence of intervention using robot, and then novel technologies to predict cognitive functions from different modalities of behavior and or physiological data. And so it's a leading biomarker studies. And now there are many other studies which try to predict cognitive functions from different modalities. And so there is a open seminar movie on the web, an AIP open seminar. And we are doing a trilateral project thanks to Tomasz. There's German and French collaborations we are doing, as well as we are also working with Karlsruhe Institute of Technology people. And one of our postdoc is now doing research there for this summer. So future work, we would like to understand mechanism and would like to develop technology to monitor the subtle change during and pre-post intervention, including cognitive load, stress, and so on. And we would like to explore cultural differences of technologies in terms of acceptance and effects. So whether we can also enhance cognitive functioning through group conversation or dialogue with a robot for Italian people or other all over the world is our interest. And we would like to call for collaboration. And please contact if you need global partner to apply IEEU project related to aging, healthcare, and cognition. So we are open to accepting researchers and postdocs as well. Thank you very much for your kind attention. And I will show, I will put this when the time for, free time, later. Thank you very much.
So thank you very much. We have time for questions.
Do you think that larger language model can have a role in this type of approaches, and what do you see their contribution in this type of clinical settings?
Yeah, actually, thanks to large language model, this robot improved its functioning. Yeah, unfortunately, my question was not answered correctly, but so we prepared the basic questions and answer data set beforehand. And so we did experiments in 2021 before ChatGPT. So we did a kind of FAQ-based dialogue system to utilize. So many questions which we prepared previously beforehand, we could answer, but questions out of pre-prepared one, the robot could not answer. But connecting to large language models, the robot answered something using large language models. So because answer is right or wrong is not the matter for this application, but rather the user make a good question or continue to ask questions and do not, lose motivation to ask questions. And so if it's achieved, and so a large language model is, for our application, is a very supported technology to improve this robot functioning. Yeah, thank you very much.
Good questions?
Can this robot be adapted to multi-language? I mean, can it speak in English and Japanese and Italian, for example, at the same time?
Yeah. So we prepared a Japanese data set in the beginning, and then so we translate it into English. And actually, we asked the professional translation company to translate into a kind of natural English. And so translation from English to other languages is relatively better translating from Japanese to other languages. So we made a moderatory natural English data set, FAQ, and storytelling. And then so we used a kind of DeepL for translating into German. And so we didn't use a kind of translation company this time. But our German collaborators checked the translated scripts and they say it's fine. So maybe fine. And so in this way, we can also use the English data set to translate into Italian. And then I hope this works moderately fine with Italian languages. So please check if we translate into Italian, and then whether it seems fine or not. And then so if you think it's fine, and then we can use these data sets to Italian older adults and or Italian people. And of course, we can answer to the unprepared questions using large language models. And then maybe large language model directly answer to the original question given in Italy and then answer in Italy. Yeah, so it's technically, basically, it's possible. Thank you.
Thank you.
As humans, our intelligence is split either as cognitive and emotional intelligence. So, and depending on the circumstances, I mean, one might be more important at the case. So from what I understood here, you applied research mainly based on cognitive intelligence. Have you thought about, I mean, towards the emotional intelligence?
Yeah,
because you said, for example, that the robot was easy to stop the or to change the conversation between the people.
Yeah.
But sometimes, based on the emotional intelligence, we might give a bit more time to a person or less time, and to manage based on what we understand about the emotions of the other person to adjust accordingly our behavior. So yeah, I mean, have you thought about towards this direction about emotional intelligence?
Yeah. Actually, before doing this formal kind of experiments, we did more exploratory experiments with real older adults. And so actually more than 10 years of continuing this group conversation session as a kind of prevention of service given by our non-profit organization of the older adults. And then so they say that doing this method, that so there is a theme every month, and then prepare the topics, and then give a talk and answer to the questions and ask questions to the others itself. It's really emotionally fine, they say. So they really enjoy group conversation. And so also we are developing a kind of system to evaluate the facial expressions as well as a kind of physiological signals during conversation, and whether this kind of intervention have a good effects in total for emotionally good or cognitively good, and is another issue. And so we intuitively found that so they are really enjoying, and so would like to continue. So it seems emotionally good effects on participants, but we need to show or collect the data that it really happens. And so thank you very much for very good points.
So thank you. Thank you again.
Thank you very much.
Okay, hello everyone. So this is Lin. So I'm a research scientist at RIKEN AIP. So I would like to briefly introduce my work on the representation learning from physical world to, the physical spare realm, is it? And to high-level correlation. So basically, maybe my background was a little bit different from you guys. My background was actually liberal education. So I took the training. In my university, I was spend a lot of time learning the Latin and ancient Greek. So today I'm very glad to find someone really Greek. Yeah, so I will involve some Greek here, so please don't point out it's wrong. So I decided not to pronounce it anymore. So, and during my university, I also took the training as a therapist. So I am a licensed therapist, but then I didn't do any practice until in 2021, I published my first paper on the clinical psychology. So I thought that I should be regarded as start practicing again. So then I did my PhD in NU and then postdoc at A-Star, NII Kyoto University, and now I'm in RIKEN AIP at University of Tokyo. So my research are threefold. First of all, because my team is in the called medical intelligence team, so I have to do a lot of medical things like involve the cardiology, the X-ray, the retinal, all the medical things you can call, but they're quite boring, I have to say. Then the interesting thing is I'm in charge of the projecting the Moonshot project. I'm currently a PI in Moonshot project. So this is a national project. So very interesting is that in vision is the human being can be free from limitation of body, brain, space, and time. So actually, it means that we are free to do any research as long as we say it's relevant to this one to help the 2015. Yeah, it's a really good thing. And finally, and also the third research direction I'm doing on the schizophrenia. Remember, I'm a therapist, so I have get $1 million project on doing this to collaborate with Zhejiang University Hospital. We're doing the subtyping and the super early diagnosis of the schizophrenia and also the other mental disorder and the other mental disorder and the things. So today I will mainly talk about the second part of research on the moonshot. So since as a therapist, so I always think of the world in a way of the from psychology way. So here is like how human do the recognition compared to machine. First of all, our human see the real world signals, which is spectral, the image, the audio things. Then in our brain, we will just decompose, or in the philosophy way, we call it constitutes the physical signal into discrete symbols. For example, like saying we have the spectral here. Let's say we have all kinds of spectral here, but then we can tell this is color, like this is red, this is yellow, or this is blue. And also we have to intuitively separate the things. For example, this is like a table, this is a chair, this is a chair, and we intuitively do it in our brain. Then after we have these symbols, then we will just abstract them into the language to say the things we can say. That's why Wittgenstein keeps on saying, just to say what you can say and don't speak anything you couldn't speak. So which means that we also may suffer information shrink into the language, what the language can be into the small language. And then from the words and sentence, people throw it into large language model. So, and during this time, from the decomposing the things, the physical world to the symbols, and into the abstracting the language, the attention mechanism plays an important role. That's why attention is all you need. Okay, so this is also explain why computer vision lagged behind. So we can say that the large language model is actually based on the human language, which has been evolved for a huge long by the 10,000 of years. So, and then the computer vision is actually directly facing the real world. Just remember the pipeline. So the large language, though the computer vision was the first one in the 2012, the computer vision starts the deep learning stage. But then we find because large language model is actually built on the human language, which is a abstract representation evolved by human beings. So now large language model take a unique advantage, advantage compared to computer vision. So in this, so as you can see, here, computer vision, we have to do a 3 megabit size things, the real physical world, and then we have to do extract feature. But large language model, intuitively we start from dealing with only less than 20 bits. So that's why large language. I think that this is one of the reasons why large language model takes such a good advantage. So I'm always interested in this part, and so that's why, as you can see, the human language-like representation now is a pivotal in the whole deep learning research. For example, in the multimodal large language model, you are trying to emerge an image into some language or into some classification, into some words. And in the generative model, it is like you have to generate this language into an image. Go back to image again. So basically, as a summary, it's like this representation, the language-like representation is a pivotal in the recent research. So what I want to do is how can we find this representation learning? So doing this one, I have following I'm following the human presentation and do the 3 steps. One is to do the physics-centric learning. One is doing the attention-centric learning to study human attention, and finally to do the human-centric learning. So the physics-centric learning is like I'm trying to find solutions to encode the physical signal into representation that is invariant to slightless resolution and things. So the solution can be both hardware and software. For example, here is like we have some doing photoacoustic imaging system. So it's a new imaging system. And also in Civil 2018, we propose a novel way to redesign the CCD of the camera. So this patent has been sold to some company. Maybe you are already using this patent already. But unfortunately, I didn't get it. I only get 1,000 yen for it. I get only $10 for this patent, thanks to this like patent system in Japan. Okay, yeah. Then like that. After that, I was doing the representation learning for to find the physical factors like illumination and resolution in the world model. So basically, we try to find a manifold. We find to build a manifold in the like the sort of like the recognition system, and then we just use the self-supervised learning to let it be invariant to the actual illumination difference and resolution difference. So they are published in the ECCV, ICCV, and actually it works quite nice. As long as you're doing anything about like low light detection or resolution detection, you have to compare with us. Otherwise, your paper will be rejected. So. And then also we are trying to, based on this understanding, we try to also extend this manifold into a generative model. For example, in our triple AI paper, we are the first one to propose a method called a lathe nerve to let the nerve to work in the dark condition. So I think that since you have the Italian, you know what is a lathe means. Yeah, do you know that? Do you know that? Oh, you're great. You forget everything in your like the great class. Okay. So basically, in the Greek, I shouldn't say anything about the Greek. The lathe means that to illuminate the world, to illustrate how the world look like. So they believe in the ancient Greek. We believe that actually this world. Why we couldn't see the things is because the world is like occupied by some like obstacles. And when you're trying to find it, you're doing a lathe, which means that which align it to remove it. So this one actually explains how nerve works, because the nerve is assume itself as self-illumination. So the nerve is like the self-illumination, which means that all the objects should be self-illuminated. So how would you explain when the light was turned off? Because the nerve setting does not have illumination at all. So we assume that the object itself, so that's why when you turn the light off, the nerve will only explain, okay, this object was moved to a faraway place. That's why all the things become dark. But we propose a second solution. So things that we're just, so we propose a second solution. We say, okay, the object itself is still illuminating, but unfortunately, for some reason, the air now has some concealing field to conceal the light from the object. That explains why all the things are dark. So when you just remove this concealing field, or you can call it the lathe, then everything becomes, now we have the light. So this is a very simple idea, like inspired by this Greek philosophy, but then it works perfectly, and now it's become like the SOTA in the nerve now. So talking about so recently in this year, we also have do a lot of research on the CVPR and the iClear, and I also hope for the ECCV, but it depends on our general chair whether you allow my paper accepted. Yeah, it's a program chair. Yeah, it's a program chair things. Yeah, so we have do a lot of things on the frequency research, on the frequency, on the stereo matching, and on the 3D Gaussian, the 3D Gaussian splitting to try to understand this physical world. The interesting thing is like that we find that we got a lot. We set up this research has like set up several sort of things. For example, our BMVC paper has 430 stars. And what surprised me most is like CVPR will be held next month, but we have already 150 stars. You can see like how people are so how people are so crazy in this, like the sparse coding, the 3D Gaussian splitting and the things. Okay, so another research we are doing is trying to do the attention-centered representation learning. Remember, attention is all you need. So we find that we try to collect the human gaze and try incorporate this human gaze into the into the computer vision. And we give us a lot of success. For example, we have achieved the SOTA performance in 2021 by incorporating this gaze on the zero-shot learning and also on the medical imaging with the limited data. And in ECV 2022, we have we also collect the world's largest the gaze dataset. So previously, all of us only know the gaze as the attention mechanism. It's all bottom up, which means given an image, you will automatically know where is the saliency or where is the attention and the things. That's why previously attention and saliency are always confused with each other. But actually our human do it in a different way. We have a top-down attention. For example, when we ask a human to classify the bird, and you can see that when the people just separate, tell the order of family, the attention is more very bottom up. But then when you're saying, okay, can you tell me whether this bird belongs to this species or that species? The human will only look at, for example, the foot or the back. So which means that actually our human attention is like a combination of bottom up and top down. This is especially important in the medical image. You will find that the doctors are trained to read the things and gaze at the image in a totally different way from the normal people. And this is exactly also the reason why the gaze research doesn't work so well before. Because we find that especially whenever we do the classification and the things, whenever it requires some professional knowledge, the attention mechanism totally changed. But the people will just only use one pattern behind it, and that's why they never success. But then, thanks to our world's largest data set on this one, and we call it Aristo. So we gave the real human gaze data set, collect the real human gaze data set on classifying different tasks. So finally, I will call it human-centric the learning. So I'm doing explore the trustworthy AI and to explain how humans make the decision, deep learning make decision, and how to enhance fairness and protecting privacy. For example, we have a pattern recognition paper, which is now I have to say a milestone in the adversarial attack on the medical image. And also we are just trying to find the pathological evidence behind how deep learning makes the decision, especially in the medical things. And also we are protecting the fairness and privacy. In our triple AI paper, we propose a way to embed this system into the camera, so the camera can protect the human face from the very beginning. So for example, if you take a photo, they will directly change the face into some famous guy. And only if you need some say, okay, this is my private image, I want to see the private, you can use some code, you can use a key to encode your own face back. And also we have to to protect the fairness, in the medical image, using the sketching or using adversarial learning, but they are quite important but boring. So finally, I want to explain. So we also have some generative model on the nerve and the things. But mainly we are interested in how to generate the image from sketch to the real image for the medical data. For example, this is also with Hataya-san. With Hataya-san, we have a paper in medical image analysis. So we are the first one to say, okay, when we do the retrieve, we propose the first retrieval system. Previously, medical retrieval system are two kinds. One is they give the text saying, okay, this is a cancer or what kind of cancer. Or you just directly compare the image, the appearance. We are the first one, you can just draw a sketch, for example, there is a tumor, looks like this one, and we find the similar tumor. So the editor's comment is saying, okay, this is not a technical improvement. This is out of the box, the concept difference and the things. Yeah, we're that. We're glad that the medical image analysis really likes our work. And also last year's Mikai, we have an oral paper on the oral paper on how to draw, how to find the image of the people, not in like the imagination, but the people to find the image in the people's mind or in the memory. For example, when the doctor like saying, okay, I find there is a disease, and what if it grows into this size? He will give a sketch, and we can just draw the real radiology image based on this sketch. So technically, it's very simple, but then from the medical one, it's very important. So this is like our style of doing the medical research. We never do any technical improvement. We really to try to solve, we do the things, try to solve like what doctor needs. Okay, so let's come back to the things, our very recent things in this year. So basically, as we can see, that when the human we go to this pipeline, we go through this pipeline. Then there is one important thing is like that, to how our human do the constitution. This constitution, for example, we can tell, okay, this is a table, or this is like a shoe. This looks appears nature, but actually it's not. So our brain have this ability to organize into coherent, meaningful, discrete units, but it's like evolved by centuries. For example, that's why we can just tell the spectral. You see, there is no color at all. But then in our culture, we just define like the spectral into the color. And for example, we can just segment the pixels into the object, or we intuitively know this is this object. And for the audio, we will decompose it into the syllables and words, and this is how the real the large language model works. And for the robotic motion data, we will always keep it like the movement, for example, grab or take, all the things. So this is a later, but actually it's not. Why it's not? Because it's important. For example, let's say for the medical thing. The medical is an important experience. The doctor will just tell you, okay, I know this tumor doesn't look good. Then when you ask him why you think it's not good, he couldn't tell. He can only say, okay, well, it looks like the shape, the star shape. But the star shape, the things is still the information appears in the knowledge. Most of the time, they can just say, I feel it's not good. But most of the time, this feeling is correct, which means that there are much things beyond our the language, but it's actually encoded our human brain. And similarly, we have also in this stereo matching, we find a very cool thing. For us, all the leaves, almost the same. It's just a lot of leaves. But for the stereo matching in the machine, they can just tell exactly each the leaf is unique. And they can easily tell it's different because you can easily find it for each leaf. You can easily correctly find its correspondence. So which means that for the machine, actually each leaf is as unique and as a separate unite as we see there is a bamboo here. And what is more, we are now working with Oxford University on the nuclear fusion research. But how would you describe a nuclear fusion? So how would you tell what is the ELM is this? And how would you describe how the movement of the plasma? Do you call it a wave? We couldn't call it a wave. So this constitution appears nature, but actually it's not, especially in the professional works. So what it looks like? It looks like that you're trying to organizing the physical signal into united. It's like painting the colors of the wings. Can you paint the color of the wings? So last year in our ICCV paper, we just do the first attempt. We try to let the machine to know how to evolve the human color perception. So very luckily, this paper got selected as an oral presentation. And then it all starts from here. So I decided to not pronounce it, not to read it anymore. Yeah, so basically in the ancient Greek, especially in the ancient Greek, the understanding of blue is totally different from our current way. For example, all of them are they think that this is the same, this color, and this color is the same. Because in the ancient Greek, there is no special blue. It only depends on the contrast of the color. So why all the language have so different kinds of the color perception? So the linguistic have a very cool research. They find that the color perception actually can evolve. So there is a very brave people go to the Lafra, which is go to it's some people in the Ghana and quoted the vote. So it finds that in 1978, the group of the Lafar have only 3 kinds of color: the red, something blue dark, and some light dark and all dark. But in the 1970s, after 40 years, they develop into 10 colors. Like for example, the 10 colors which were very similar to what we are using in our language. Why? What makes the difference? So according to some research, they think that because it is what drives the evolution of color naming is because it is under the pressure of communication efficiency and perceptual structure. So what is the communication efficiency? I think this is a perfect manga to explain it. For example, like that, so this people is told, okay, we find a terrorist, and finally he admits that you have which Y to cut. But it's a magenta cut. What? It's a magenta Y. So which should you cut? Which means that for the why we have the color perception, which means that the color should indicate exactly the correct things. Otherwise, you will be bombed, and then luckily your gene will not exist. It will be derived anymore. So you're evolved. So our language, our color perception our color have to describe the spectrum into the correct way that you can use the language to indicate it. So you have to, it means that you have to communication efficient. You have to communicate accurately, and you have to use as small number of the color as possible. So like then we can just solve it very simple, like the smaller color size, while we have to use a smaller color size, as many small color size as possible, and have higher accuracy on this limited color size. So this is in computer vision. It's simple. It's called color quantization, and then we just do the color quantization and do a high-level recognition. Just try to use the 2 laws: one up, push down. Then it's done. And here is our result. So this here, we just developed the color expected by linguistic. And this is, I think, the coolest one. This is a real different color distribution in different language. And this is what we automatically evolve by ourselves. And we find that this is the theoretical accuracy of the language, upper limit. And there is the actual language. And our accuracy is very similar pattern as them. So here is like our result, which can do the evolution and the things. Yeah, finally, as a summary, in 2023, we have 16 top conference papers like the CVPR, like ICCV and the things. And we also have a later method published, accepted in this direction. And we hope that we can have some more collaboration on this exciting field. So thank you for your listening.
Thank you very much for your very nice talk. There's time for questions. I have a question. Sorry. Okay. Okay. Go first.
Yes.
No, I was wondering. I remember from when I was reading about colors that the RGB systems cannot represent all possible colors that we perceive. Is this any constraints that you also have in your system?
Currently, now we don't have this problem, because you see the human's color perception, in the culturally when we classify different color is still very rough. So we have not yet reached that field. But of course, you're right. You're saying is very correct, because for example, the machine, and if we have not the RGB, for example, we have hyperspectral camera, then we have to consider that. Yeah, that's why we have to use evolution to go beyond the existing human RGB system.
Thank you.
Yeah, thank you very much for the enthusiastic talk. So I believe that you definitely expert of representation learning. So from the figures of human learning, like the way we use attention lag to how we encode the modalities, the input data, right? So it seemed like transformers is basically a good candidate. It decouples from data and architecture. So it is like data agnostic, right? So there's a trend, like we just use a different kind of tokenizer to tokenize the modalities from different kind of data. So, and then we use transformer to learn on kind of input like this. So what do you think about this trend?
Oh, yes, so that's why we call it the, I say this part is actually a tokenization. Yes. I think that with this evolution way, we can also do it for the robot and things. Actually, we are now working on this field. So if there is any I'm looking forward for any collaboration.
Yeah. So the key here is to find the right tokenizer, right?
Yes. If it's in the large language model way, we will call it the right tokenization.
Yeah, thank you very much.
Thank you.
Other questions?
Just to follow a bit more the general picture, at a certain point, the first part, you were talking about invariants, and then later on about tokenization. So which is relation between the invariants you can extract from the first stages and the tokenization aspects? Would are them linked together somehow, or they are not?
I think that I can only say to explore it in different way. So one is like to do the physical things, but the tokenization, because you say large language model only emerged like in this recent years. We find that maybe so we should do it in the tokenization way, but we haven't like published any paper on the tokenization yet. But I think that maybe the methodology is the same, but then the actual thing is quite different.
Okay. Any other question? If not, we can thank again.
Okay, thank you.
Thank you again.
Thank you for the surviving to the end of the session. I will try not to crash with the dinner, although I have many slides, and I will try to show you the story, which is kind of following Mihoko's story from the previous talk about our laboratory approaches to help elderly people. Okay. So basically, I will try to show you our introduction to our lab and our concept to having kind of end-to-end laboratory. We are designing experiments, we are running experiments, and we are processing the data. So basically, we are very open to collaboration with all these fields. As we started a long time ago, I started my research from the so-called reactive BCI, brain-computer interface, which I will show you some examples. Now we are moving slowly to passive BCI, which basically I think is very close to also what you do in Italy. Marta was showing today morning this cognitive control, cognitive monitoring. That's what we also do. It's called passive brain-computer interface. And also I will show you some of different modalities we use in our experiments. You are welcome to visit our website. So this is BCI Lab Info, where basically all this brainy stuff is being presented. And also just to show you kind of like, a little bit advertisement, we ran like 2 weeks ago, BCI and Neurotechnology summer school, spring school, which basically attracted this year 82,000 people So basically it really shows how many people via Zoom is helping to do those things. Like last year we had 15,000, 2 years ago there were 5,000. So basically it really shows how people are interested these days in BCI, thanks to Elon Musk also, who is doing great advertisement, but basically mostly because of development of the machine learning tools. On the hardware side, there is no such a big jump, but due to machine learning, more students are very much interested, there is more data available. So basically I think I would like to promote the field. So let me show you quickly some of our former BCI projects. So basically those are the different modalities. We can record EEG, we can record eye tracking, we can record optical flow in the blood using FNIRS, and also we can use like eye movement, etc. So basically what I very much promote, instead of using artificial intelligence, which would be reproducing of the human beings, we want to develop intelligence augmentation, IA, which basically will help the people and basically do the technology to do as positive things as possible, not like these days language models, which could be hallucinate and doing some negative outputs. So basically, I will show you some examples using different modalities. We use visual modality, we use auditory modalities, we use also touch sensation. And these days, luckily, due to, again, development in the hardware, we also use olfactory or smell sensation, and I will show you at the very end. And due to this kind of new development in smell aroma stimulation, also Panasonic will join, come very soon to our laboratory because they want to also together develop some new stimulation modalities. So what we did in the BCI, we very much utilize some of the brain responses. The most famous one would be P300. So around 300 milliseconds from the onset of the stimuli, if this is your target, our brain fires this beautiful response. If we ignore it, there will be flat wave in this case. We call it beautiful, but this is 6 microvolts. So this is 10 power minus 6. It's a teeny tiny signal. So that's why signal processing, machine learning, it's super important to squeeze the data from all the noisy, like the signals we record on the level of our skin on the head. Also, we know from our previous experiment that when we modulate the cognitive load, when subject will be tired, this response is changing. And this is very similar to what happened with aging. People, when they age, every stimuli is kind of causing more cognitive load. So basically, we can really distinguish in this case from the shape of this brain response if this person is easily processing the data or simulation or not. So previously in the BCIs, my students at the University of Tsukuba, they developed really beautifully many examples. We use auditory BCIs for use for spelling. So those would be the kind of classical brain-computer interfaces. We use also tactile, punch sensation. Again, we stimulate the people. And we could ride wheelchairs, doing some robotic stuff. You can see some walking robots and so on. As I mentioned before, those robots were falling a lot. So this was the most of the problem. But what was also interesting, already 10 years ago, with Professor Furukawa from the Tokyo University of the Arts here in Tokyo, we developed also a so-called active BCI, when subject was thinking about some musical phrases. In this case, there were only 5 commands, and this was already 10 years ago. So luckily now we are again talking to Furukawa, and we will be developing completely new musical brain-computer interface. But let me play you what was done 10 years ago. So I hope you will hear it. So in this example, our brain musician is wearing EEG cap, and he is thinking about 5 different notes. And in that case, he was playing together with real musicians. So there was a special composition slowly developed, because we need like at least 1 second for the classification. So you cannot play rock and roll, but this kind of easy, relaxing music was played. And this was done in public. So this was in the concert hall of the Tokyo University of the Arts. So it was really possible already 10 years ago. But we had only 1 subject who was training for half a year, and basically we had only 1. So there was no paper, there was only demo. So I hope we can do it better, and maybe we can also do it for the elderly people, because we are very much interested in defining the early onset of dementia. So basically, early onset means like somebody who is 40 or 50 years old, because that's a time when we can plug in some intervention. If you're already 70 and you have like, age-related dementia, maybe there is not so much hope for the help. So as already Mihoko mentioned at the beginning of this session today in the afternoon, even like United Nations have one of the goals, good health and well-being for everybody. This beautifully is fitting also the AI for social good. So basically, we would like to contribute to these developments. And the numbers are really bad. So basically, number of dementia cases are rising, like, families are suffering. Very often we have to remember that quite often the family member, they suffer more than actually the person who is suffering from dementia. So also we can relieve the health system, because we will help those people who are taking care of people with dementia. There is no drug, so all the pharma industry failed badly. There is no chemical compound that could help. But already like World Health Organization is showing that quite many non-pharmacological interventions which we can consider. Changing lifestyle, changing your diet, changing your intellectual life, social life. But sometimes we don't know what is fitting whom. So that's why we want to develop this kind of practical biomarker that people could use at home. So they would be not like a laboratory style, but really wearable in this case. And those elderly persons, as these days we measure blood pressure, we measure this kind of basic biomarkers. Some people have Apple Watch with ECG and so on. We can do it at home. So basically this would be this kind of like a brain fitness monitoring. But still, like, we have some way to go. So when we think about the like Alzheimer's or like, heavy dementia, this is actually practically shrinking of the brain. But still, aging is also causing some shrinking, but some people still have very good cognitive skills. So basically, we want to measure it. We want to find the onset between the healthy and this kind of beginning of the trouble, because then when this kind of non-pharmacological intervention could work. And we also have to remember that quite many of dementias, when we quite often think about dementia, there will be Alzheimer's-type dementia, so basically damage of the brain structure. But this will be like 60 to 70% of the cases. 10 to 20% is so-called vascular dementia, so basically damage of our vascular system, heart diseases, and so on inside the brain. And the main complexity is that actually majority of the cases actually are kind of mixed. Somebody has a little bit of vascular dementia and a little bit of Alzheimer's. So basically, like, if we can measure both of them, that would be really fantastic. And we really postulated Alzheimer's-type dementia, we can measure it with electrical activity, which is EEG, already 100 years old technology used in the neurology, etc. Vascular dementia, blood flow, this one we can measure with FNIRS. And luckily in this laboratory here, across the wall, we have both devices and we can measure it. And I will show you next. Also, recent, in this area publication, 2020 Lancet Commission report, was already postulating that we have quite many non-pharmacological interventions we can plug in. And basically, the first report was 2017. 2 years later, they published next one, and they identified much more intervention which you can switch in the mid of life, on late life, basically to change, improve your well-being, and prevent dementia. Nothing is pharmacological. This is all lifestyle changes which can really contribute to your well-being. And also we know from the neuroscience research that quite many candidates of different biomarkers evoke potentials spectral parameters and so on, which we can potentially use. But we know that in daily life, this sometimes is difficult to measure at home. And as I said, we have also FNIRS, which basically we can measure the blood oxygenation just in the surface under the skin. It's safe. This is like infrared illumination and reading the responses. But it's also quite good to kind of evaluate how well the oxygen is circulating and blood system under it. So basically, to follow all our fathers, we kind of postulate that we can measure something what is measurable and make it measurable if it's not. If you can measure it, you can improve it. So basically having this engineering approach. So these days, unfortunately, majority of the cases we have to do with this kind of paper and pencil test. Annoying, super subjective, we cannot do it every day. So that's our proposal to replace it with this kind of sub-objective, home-based experiments. In laboratory, this would be like EEG and FNIRS. So basically, this would be some electrodes measuring electrical activity and some of the optical sensors, which could be integrated in the single cup, so it's quite practical. We want to move it into a kind of home-based wearable, where basically elderly person using TV, maybe touchpad, could do such experiments, maybe once a week to kind of evaluate what's going on, because maybe they could be trying different interventions. So the most simple experiment would be so-called oddball paradigm used in the BCI. When we ask somebody to remember a picture, and then we showed kind of series of the random pictures, and basically well-functioning brain will remember this picture and fire this aha response. If somebody has very bad short-term memory, it will be forgotten immediately. So there is no this response. But also at the beginning, we also ask our subject to use the button press just to evaluate if they understand the experiment. And already from the behavioral responses, we could see differences between our healthy aging people and those with the MoCA score. So basically already reaction times would be showing. But as you can really see, those distributions are really huge, so we couldn't use it for the machine learning. That's why using the brain activity, it's much better, because the difference between those aha responses, so there will be the red one and the bluish one, different electrodes, it really shows healthy people versus those who have memory problems. And this is already something we published several years ago, but it really shows that actually it's really worth to use different machine learning algorithms. Shallow learning was kind of running just above the chance level, not so fantastic, using some deep learning algorithm, and that would be like with Chibin's laboratory. We developed this kind of tensor-based improvement of the deep learning. And that time we could jump to 80%. These days we can do it much better. So this is our recently published papers. We publish this in the Frontiers in Human Neuroscience. So basically, in this case, we show how machine learning could be used for the early onset of dementia using network topology features. So this is kind of very hot topic recently in the neuroscience, kind of modeling the signal as a graph. So basically, this is our system setup. We're using GTEx system. So basically, if somebody knows MATLAB, this would be kind of nice Simulink setup when we can get all the data. This one was using with LSL. So Simon is here. He developed also this part. What we do in the neural network neuroscience approach, we basically take the raw signals and we model them as network. So this is quite simple. So we are basically sliding the kind of embedding window, and we kind of convert our real signal into those kind of vectors of the permutations. Those permutations kind of are building graphs. So basically, we can evaluate how the signal is repetitive, if it's returning to the same graph point or not. So what is really a result of that, there will be kind of messy graphs when the very complex signal would have a lot of nodes and a lot of edges. When simple to predict signal, this would be kind of extreme in this case, which could be modeled from this simple graphs and having less edges and nodes. So we did experiment. Again, remember, we want to kind of distinguish people who have strong cognitive skills with those weakest ones. That's why we developed different paradigms, which we kind of a little bit put a pressure on them. So first paradigm is kind of for our Japanese subject, but also works very well in our Western subject in Poland. We train our subject to evaluate emotions. So we showed them short videos. As a next step, as usually in psychology, we judge each emotion using this kind of two-dimensional grid. So basically of the valence and the arousal. That's what psychologists do, but usually people, we don't do it. So we believe this is a new skill. We ask them to learn very quickly. So basically in the training case, there is a video. We show them when this emotion is classified, and we ask them just touch and just to use it copy paste. In the second run evaluation, there would be no this kind of prompt. So we show them video and immediately ask them, please remember when this emotion, there is a different video. So basically same emotion, but there would be different person. Those are the actors. So let me show you this quick video, how the experiment runs. And since this is so-called dual task, we don't care so much about mistakes they can make. We just give them tasks to kind of put a pressure on them. And it's kind of quite cheerful. So this rounds, we have let's say 40 kind of pictures or videos, and they do it by themselves, touching and so on. And we record EEG. In the second task, we did it also simple. We use so-called reminiscent images. So we know that elderly people have kind of preferences for the interiors from the past, from the childhood, and so on. So we kind of mix up this experiment, which is shorter, just showing the pictures, showing pictures like would be old Japanese style from the Showa era, so the childhood of our subjects. Same style for the Western, modern Japanese and modern Western. When we ask them about the preferences, immediately Japanese pictures are winning. They are really preferred. They feel good watching those pictures. They're really uncomfortable watching those modern ones. So it's kind of really showing we really put some pressure, which really works well. So as a result, in these papers, we could beautifully see that using this network topology approach, we would really see that our networks modeling those EEG channels, we do it everything separately, so we can really see which part of the brain possibly is contributing the most. And we can really see those are statistically significant differences. So basically, brains of the cognitively strong people, we evaluate them with the paper and pencil test, and those who are weaker, really kind of different. And it's really nicely reproducible with different tasks. So it's kind of a little bit task independent, which is quite good. What was also nice, one of the electrodes, which was kind of tricky, we know because many of our subjects are female subjects. Females have more hair in the back, so basically this electrode was flying out and was resulting with noise. So kind of confirm also our setup. So there would be on the statistical side, there would be significantly different. When we do clustering, this is unsupervised clustering using HUMA. You can really see we can beautifully separate those kind of two responses. So healthy would be blue, MCI would be orange. Some of the subjects kind of end up on the different side. This could be a mistake because paper and pencil tests would have some mistake or still it's imperfect. But when we jump everything for the classification, this will be leave one subject out cross validation. So basically we train on the rest and kind of evaluate on our subject. We are kind of reaching 90%, which is good. Still not industrial level, which would be 95 plus, but it's quite okay. So in our subsequent paper, and also just to show you that we still don't have enough subjects covering all our cognitive scores, in this experiment, ages of the subject will be from 81 to 61. So maybe not so early onset, but still those people really want to know how well their brains are working. We kind of extended this to topological, in this case, data analysis, so TDA. Another hot topic, which was recently introduced in the Royal Society, Open Society paper by Olaf Spons and his colleagues. So in this case, again, we process our data first separately with different channels. We only use 8 channels. This will be front of the head, so we mostly focus on those areas which we know are kind of sensitive for the dementia development, so the temporal cortices and also a little bit parietal. So we remove all the artifacts, kind of classical EEG processing. And then we kind of form multi-channel point of cloud. So basically 8 channel, 8 dimensions. And then we try to evaluate it using classical TDA features, so maximum number of cycles, persistent entropy, et cetera, et cetera. So kind of typical judgment of this point of cloud, which is used in the TDA. And when we look at the results, again, majority of those features beautifully already separate statistically. So we can really see differences in the complexity of the EEG of the healthy or normal brains versus those running into trouble. Again, when we do this for this using clustering, so in this case, we could separate because this was the experiment when we had some target images, non-target, and all together. Using UMAP, starting from targets, kind of separable. Using non-targets, so those are the simulation we ask subject to ignore. Sometimes in dementia, in aging, ignoring something, it's more difficult actually than processing, because they have to kind of like, use more resources. So basically, this separation would become better when we use all together. We can really see it's kind of very close to those kind of non-targets. In our audible experiments, we have more non-targets than targets. So this also maybe helps with training those clustering. When we use TSNE, which is kind of like having trouble with the initialization, you can really see this kind of reproduction of this result is not so clear. So basically, this is kind of showing that UMAP would be better. But what is also very nice, once we process with UMAP, so basically dimensional reduction, we can jump accuracy for different subsets from 95% for target for altogether 93%. What was also very good, we also tried using regression, because basically being kind of binary, you don't want to know that one day you are MCI and second day you are okay. Using regression, because MOCA scores are continuous from 0 to 30, and usually 25 is the onset. When we use regression, we can have nice median absolute error plus minus 2.5. So it's quite good because it's kind of close to human beings. Those scores are also non-perfect. So basically being on this error level of plus minus 2 is, I think, quite okay. And having percentage error around 10%, it's quite good. When we are submitting this paper, the reviewer gave us really hard time to kind of try all possible classifiers. Our choice was random forest classifier, which kind of performing with the best. But also, as you can see, majority of the classifiers are quite okay. You can really see deep learning is kind of suffering on the targets because we have more examples. So basically, deep learning will be data hungry. Random forest is sometimes you can really see even reaching 100%. Again, this is leave one out, cross-validation from our around 30 subjects. Great, I have still time. As I see, so this was electrical activity of the brain, targeting Alzheimer. Second one would be looking at our vascular in the escape part. So basically, we want to see how well the vascular system is developing. It's really known in the neuroscience, in the in the healthcare, that high blood pressure, obesity, diabetes, and so on, all these kind of civilization-related diseases are causing vascular problems, and this is leading to dementia. So basically, avoiding those problems would be the main target. We know from the anatomy that actually our neural system is closely related to our vascular system. So basically, if vascular system doesn't work well, our brain definitely will not. Again, using our system, this would be again our single link model. So we have our FNIRS, equipment, everything is by GTEC, and the EEG amplifier, everything combined together and recorded all together. So this will be the experiment example. So again, using our favorite database of the emotional expressions. And as you see, this is the FNIRS module, and this is the EEG module, and basically electrodes on the head. So again, this is laboratory setup. We really want to move it to kind of more home-based setup. As I say home base, you can do it by yourself. So basically, I'm putting this gel by myself. The main problem is about EEG and FNIRS. There would be completely different temporal resolution. EEG would be on the second level, and we have sampling 200 hertz. FNIRS is only 10 hertz, and we need 5 or 10 seconds. So basically, these days, we can do it with machine learning. We can really merge them together. So this will be our another paradigm, which I would like to quickly introduce, the so-called fastball paradigm. So this one is very nice because it's kind of instructionless paradigm. So at the beginning, when we start experiments, subject can see, but we don't tell them anything, one of the pictures. So this is kind of slot pictures, and we don't give any instructions. After that, the kind of quick run of this flashing picture is showing. This is like a 5 hertz, so 5 pictures per second. But our secret target pictures, it's always showing up at the exactly same position. Again, people who have still strong short-term memory or working memory would have nice kind of automatic response because the brain remembers. Again, in this case, we are using both modalities. There will be FNIRS and the EEG. So this is the comparison of the responses. Somebody who has good working memory will have kind of the difference between this kind of standard stimulation and when the target is showing up. Again, very small, it would be 2-3 microvolts difference, but we can really see it. Subjects who have very weak, in this case, working memory, there will be no difference between stimulation with the target and the non-target. So it's quite good, just you can do it 1 minute and you can have showing example. this could be also related to kind of like cognitive load, tiredness, and so on. So we have to be careful. But basically, it's showing performance of your working memory, which is a symptom of the upcoming dementia, or basically maybe post-COVID problems and so on. Also, as kind of example advertisement, we compare different EEG systems. So basically, this one would be kind of clinical level EEG system, beautiful difference. This would be Unicorn, so one of these GTech products, which is using dry electrodes. So it's kind of in between wearable and kind of clinical. And basically using complete wearable, this is called Muse Band. It's something you can buy for $200, but you can really see there is something going on. So basically there's a hope that we can use this paradigm with really kind of very low level wearable for the EEG. And when you look at the FNIRS, this is still very preliminary, but we can really see changes between our healthy subject, which will have kind of at the beginning drop of the oxygenation, and then they return. So basically maybe at the beginning of the paradigm, but this is 10 seconds long, so we have to be like, careful. And our subject who have MCI, which would have the opposite, like in this case pattern. So basically it's showing blood oxygenation is also showing different dynamic, but all completely different time scale. And for the last 3 minutes, our favorite paradigm these days is olfaction. So basically this one is showing very recent paper also from last year showing that overnight, and I would really recommend, my mother is using this and she's loving it. Basically overnight stimulation, you switch on overnight this kind of small like diffuser of the smell. Our olfactory system is also working at night. In this experiment, they use every night different smell. So maybe this would be the clue. So basically you go to sleep, you switch on for 2 hours, you're like, ultrasonic, like, with some drops of the natural smells. And with the elderly, they can really see dramatic change in the cognitive performance. So it's a beautiful overnight stimulation. And they even show it, like, for that group, but over several months, this kind of effect is like, staying. What is really, really important and interesting, first thing is actually our olfactory bulb, our system for the smell detection, which could be very much impacted by COVID and many kind of viral infections, also important. So we have to take care of it. But it's also good because it's kind of outside the brain. So we can easily measure it like, here, and I will show you the method developed also recently. But what is the most important, the olfaction smell, is the only sense that have direct connection to our hippocampus. Hippocampus is the kind of our structure of the brain which is first impacted by aging or dementia. So like, shrinking of the hippocampus is problem with the short-term memory. So imagine overnight you can stimulate your hippocampus and make it grow, physically grow, which is kind of nice trick. Only smell, only olfaction is the sense which we sometimes don't maybe think much about. So like 2 years ago, our colleagues from Karolinska Institute, we kind of try and like establish collaboration with them, develop new methods when they put the EEG electrodes exactly over the olfactory bulb. So as I told you, luckily that part is kind of isolated from the brain, but it's part of the brain. And using high frequency, in this case EEG, they can really detect changes related to the smell, like simulation. So we developed it, and this is for the Nicolaus Copernicus University in Torun, our collaborators. Luckily, they had already this kind of beautiful device, little noisy, which basically allows to kind of stimulate subject with 6 different scents. So basically, they are kind of like, some small jars which would have different smell, and through the pipe, we can precisely stimulate our subject with different smells, which was always kind of headache to develop, but these days are devices. So we basically, for this paper, which will be presented soon in Yokohama at the IJCNN, so this is Hubert Kasprzak, our Polish student who developed everything and runs it. We're using CSP, so this is classical using the BCI method for kind of training spatial filters. We basically find the electrodes which are contributing the best based on the maximizing, minimizing the variance. So we can really see, and this is also nice comparison, relation to previous publication, but mostly in the kind of so-called temporal cortex on the right side, we could see kind of significant changes which contribute to the classification. So basically it's kind of showing that this part is working on the olfaction. Again, we try to do it for our clustering. And in this case, we kind of ask subject to remember one smell. This was done with students, so those are the young people. And basically we can separate them with different frequency bands. As granted for the classification, there is a little bit headache because experiment was a little difficult. So unfortunately, half of our subjects using only EEG were at the chance level. So the BCI would not work. One subject was 100%. This is within the subject, in this case, training. And some subject would be beautifully performing, so they can do it. This was when we used only EEG. So in the subsequent paper, we also showed that adding EBG, this kind of like electrical activity focusing on our olfactory bulb, so you can see that those electrodes beautifully also contribute using those CSP filters. So we have still activity in our temporal cortex, it's fine. Plus we have activity contributing from those olfactory centers. In this case, we compare that when we do EEG only, we are kind of on the median on the chance level, but when we combine those modalities like smell-related electrical activity and the brain activity, we can beautifully go on the median above chance level, and majority of the subject can do it. So the final paper and the final result, since so many subjects were running on the chance level, we kind of divided into two groups. Those who will be like, say, low performance, so like, on the low cognitive attention, and others who will be like, performing well. And we try to see from the EEG, we can predict how the subject will be performing on this BCI task, which was kind of difficult for the young people. So we tried this using only those EBG electrodes, only two frontal electrodes, and those will be two nice, completely visually differing patterns. When we use only EEG again, but this is like, not focusing on the smell, but focusing on the attention. So this pattern is different than the previous one on the temporal cortex. But it's kind of showing now like, this kind of differences. And again, when we combine EEG and EBG, they would be quite nice, also differing pattern. So this is good when we go for the classification. Again, we evaluated many classifiers, deep learning, and maybe again, random forest would be the best. And combine both modalities would be like, almost scoring 100%. This is again, binary classification, good performer versus bad performer. Second one would be only using EEG, and this EBG on the two electrodes would be closer. Chance level in this experiment would be 70% because our subjects were not equally distributed. And finally, we also tried the eye tracking. So that would be the final modality. We know from the previous publication that the pupil size, pupil level, is related to our self-control. So basically, we don't look at the kind of where the subject is looking. We only look at the kind of condition of the eye. It's very easy to set up. These days, eye trackers are small devices, which you can put. So we also use this kind of like robot smart speaker for the experiment sometimes. And we can use also the eye tracker. And preliminary results are very good. Again, using this kind of like network neuroscience approach, we can really see, we can distinguish our low performing from high performing subjects. So basically dynamics of the pupil size, which could be measured with the 60 Hertz accuracy, is useful. So just to summarize, I hope I convince you that it's really worth to return to BCI. 80,000 students are willing to do it from around the world. This is also nice because we had people coming from 118 countries. So basically it's really showing doing this Zoom kind of summer school or spring school. This is supported by GTech, but we all kind of contribute for that. And basically machine learning is now kind of giving now again possibility. Elon Musk has a big company, and also some other big names are returning like Sejnowski, etc. They are publishing now papers on the BCI. And as I said, we have this kind of higher goal. We really want to support our aging society. I think Italy in Europe is the first aging country, followed by France, I think, and Germany. So this is also a topic maybe for our collaboration. Robots would be great for that. And yeah, we are very much excited and open for collaboration. We just finished this kind of German, French, Japanese project. Maybe future one would be Japanese and Italian. Thank you very much.
Thank you very much. Questions?
So mine is more or less a curiosity than other, but what I catch from your presentation is that a bit we are going also to use the spatial of the sensor, and so to use and to try to intersect the cross correlation between all the different ECG channels, pretty much.
Yes, because special filters, they finally use this kind of similarity measure. Yes. So it's kind of more complex than just correlation, but yes, sure.
Yeah, sure, it's
sure.
Multiple. Okay, thanks.
It's also showing us that we can use less sensors because some of them are really contributing. But this is also kind of a way to finding which part of the brain or which electrode location is the best one. As I told you, we want to use a wearable. So there would be definitely less electrodes for that.
So thank you very much for your presentation. So I'm not really an expert, so my also is a little bit of curiosity. So it seems that there are studies showing the relationship between Alzheimer-like diseases with insulin resistance. So I was just I was just wondering if you think that having more invasive measurements might also help predicting the occurrence of neurodegenerative diseases.
So yeah, so just to comment, some medical doctors say that Alzheimer is diabetes number 3. We have 1, 2, and this is the third one. So basically, this is really metabolic problem, like inside. But still not know if this is result or this is a cause. But basically, yeah, definitely this is related. And yes, invasive, beautiful signals. I wish to, but please find me candidates who want to open their brains, like So basically, this is maximum. And even doing EEG, some people complain, like it's like because you put something on the head, it's squeezing your head, and so on. Some people don't know how much information are reading. So basically, I think this is maximum what we can do. That's why, like also eye tracking, maybe not perfect, but this is maybe the less invasive modality. Like if this pupil size dynamics would give us enough information, this could be something that could be in the glasses. This could be in the computer screen. So yes, we want to make it as less invasive. I hope machine learning will help with all the noises, but I don't think people will be like willing to open their brains. So yeah, practical application.
Okay, any other question? If not, let's thank again.
Thank you very much.
Speaker.